So hi everyone, can you hear me?
Yes, sir.
Okay. Is there anyone from NPTEL in this recording? I was told that a Mr. Arun Kumar would be present during the recording. Mr. Arun Kumar, are you present? Uh, okay, so recording has started. So there are 40 participants. Uh, okay, so let's maybe wait for 1 more minute. I'll share my screen in the meantime. Uh, can you enable screen sharing for me? I'm trying to join through my iPad, but I cannot share my screen. Can you please check?
Yes, Professor, you can see your screen.
Okay, nice. Okay, then maybe we can get started. Yeah, there are a little, yeah, about 60 participants. Okay, so hi everyone. I'm Pranay, and this is the Foundational Math for ML course, Optimization Part 2. The Part 1 was taught by Professor Jaykrishnan Nair from IIT Bombay Electrical Engineering Department, and this is Part 2. Uh, So, uh, a few quick announcements. One is that I won't be able to actively monitor the chat. So, I would encourage you to answer each other's questions if you can. And what we will do is every few minutes, I will uh, ask for if there are any questions, and we can have questions for few minutes, and then we will continue. Okay. And then we'll go for around 90 minutes. Then we'll have a 15-minute break. And then we'll have another 90 minutes, followed by a 15-minute break. And then we'll go for another 1 hour. Okay. So 90 minutes, then 15 minutes break, then 90 minutes, again 15 minutes break, and then 1 hour. So we hope to finish around 1:30 p.m. Okay. Uh, Another thing. So uh, I injured my shoulder last night. So I have to sit very still and I cannot move around a lot, like otherwise it hurts a lot. So after some point, I might switch off my camera and yeah, I'm still around. You will be hearing my voice. This is just because I have to sit very still and I don't want to make any sudden movements. Yeah. So I was not sure I'll be able to teach this class, but if I sit very still, I am able to function. Okay. Okay. So let's begin. Uh, so uh, we will start with some motivating application. So we will use linear regression as a motivating application. Yeah, we will use linear regression as a motivating application. I will spend some time talking about linear regression because it is like one of the essential things you learn in ML. So it is good to get some background. I will not cover it in too much detail, but it will sort of become the running theme for this entire course. Okay, so we will start with some very simple settings and then develop some algorithms. And then we will realize that when are those algorithms insufficient, and we will generalize our existing algorithms or come up with some better algorithms to go ahead. Okay. Then, based on this motivation, we will go to gradient descent, which is like the most important algorithm we will study in this course. So, most of today will be dedicated to gradient descent. Okay. For that, we will require convexity. So, those of you who have done the part one of optimization with Professor Nair, this will be a recap for you. Although I think there will be something which you will find useful and which is like a unique perspective on convexity. Next, we will go to smoothness. So this is again a very useful property of functions when we are studying optimization. So we will look at this. And finally, like probably this will be by the end of today. We will look at some convergence results for some common function classes. Okay. So when does gradient descent converge? Does it converge or not? What are the assumptions we need for it to converge and so on? Okay. And then tomorrow we will look at some of the advanced algorithms. So we will go gradient descent, beyond gradient descent. So we might look at momentum. We will definitely look at SGD, which is stochastic gradient descent, which is like the workhorse of modern machine learning. I would have liked to cover some advanced algorithms which build on top of SGD. I think I mentioned it in the contents of the course, such as AdamW, etc. However, I don't know if we will have enough time to cover all of this. If we don't, then I would love to like teach another sequence of a similar course in which we look at more advanced algorithms. Okay. And then finally, I think this would be by the end of tomorrow. We would look at what happens when you have to do computations in a distributed setting. So distributed computation, this involves things like distributed SGD. This involves things like federated learning, for those of you who have heard the term. Uh, so just an aside, uh, most of you must be using either Android smartphones or iPhones. Both Android iPhones as well as iPhones and Android smartphones as well as iPhones use this federated learning to train their smart next word prediction engines. So both Google as well as Apple deploy this thing. Okay, so I really hope we can get to federated learning by the end of tomorrow. Okay. Yeah, so for today, we'll be looking at linear regression. And for that, we will be looking at a specific data set to motivate the kind of application we require. Uh, so I suspect many of you have already taken the first two courses in the sequence, which were linear algebra and optimization part one. So I won't cover a lot of either of them, but I will recap some of the fundamentals as and when we need it. Okay. So I will recap some linear algebra, only the bits that we need. And I will also require some vector calculus. I will state the results without going into a lot of details of them. Okay. So if there is any interest, I can provide some references for whatever I cover. Okay. And then I'll go to gradient descent, convexity, etc., which will be like the rest of the lecture today. Okay. So for linear regression, a good example, in my opinion, is something called the California housing dataset. Okay. So this, as the name suggests, this is about houses in the state of California. Incidentally, I'm currently in the state of California in US. So the the objective of this data set is to predict the median house values for California districts. So a district in US is roughly similar to what districts in India are. So we are interested in looking at the different districts in the state of California and predicting what are the median uh, costs of houses in a specific district. And we are supposed to predict this in multiples of $100,000. Okay. So this data set contains these many, about 20,000 entries, and there are 8 attributes corresponding to each block. So there are 20,000 blocks. A block is like, think of it, a think of an analog in the Indian context as a student hostel or a couple of student hostels would be one block, or a street would be sort of one block. Okay, so this data set contains 20,000 entries, which are entries for 20,000 blocks. And for each block, there are 8 entries which look like this. So for each block, they give you what is the median income of a household. They give you how old the house is. So this is the median house age. What is the average number of rooms per house? What is the average number of bedrooms? And so on. And they also have a block average of what is the like median value of houses in a specific block. Okay. And this is used to train like models to predict what are the values of houses in a specific region. Okay. Okay. So, like a simple way to think about it is, if you are given like such a data set, you might first come up with some heuristics that how do you predict the value of a house. So one simple heuristic is that you look at the number of bedrooms in the house, and let us call this as X. We multiply that by the cost of each bedroom. So let's call this theta 1. So this is sort of the cost of all the bedrooms in the house. And then we add some fixed cost, because you have to lay the foundation, you have to do some registration once the house is built, and so on. So this is a very crude estimate of how you would estimate the price of a house. You take the number of bedrooms, you multiply it by the cost of building a bedroom, and then you add some fixed cost. Okay. So as you can imagine, like this is a very crude estimate, but this gives us one starting point. So to express it mathematically, our very first model of house prices is we denote it by f of theta. So f of theta is our model for house prices. X is the attributes corresponding to a specific house. Okay. And we have two parameters, theta 1, which is the cost per bedroom, and theta 0, which is the fixed cost. Okay. So this gives us a very simplistic model. And as you can imagine, this won't be very accurate, because there are a number of factors which go into deciding the price of a house. Okay. So you might ask, why only number of bedrooms? Okay. You might ask, why not the population of the neighborhood? So if the neighborhood is very crowded, maybe the houses are not very highly valued. Also, if the neighborhood has no people, the valuation is also going to go down. Okay. So there has to be enough number of people, but not too many. Similarly, not just the number of bedrooms, in general, how many rooms are in that house would decide what the value of that house is. The location would also govern some amount of value of the house. So, for example, if in a city like Mumbai, is it close to a metro station? Is it close to a shopping center? And so on. These will also drive up or down the price of a house. So, interestingly, if you look at this data set, they have two attributes called uh, latitude and longitude. And the reason for that is that people in California, so California is a coastal state, and people in the US love to go to the beach. So the closer your house is to the beach, that is decided by the latitude and longitude, that will drive up the price of your house. So houses in California which are right at the beach are some of the most expensive houses in the world. Okay. So in general, like as we just discussed, that rather than looking at a single feature, which is the number of bedrooms, we care about and we might want to care about a lot more features. And these are some of the examples. And in general, it is usually good to have more features. Okay. So just to put things mathematically, suppose we have a feature vector which has, let's say, d minus 1 features. So x bar, anything with a bar above will be used to denote a vector. So let me write that down here. So x bar denotes vector. And the dimension of this vector will be clear from the context, or I'll specify what the dimension is. So in this case, let's say there are d minus 1 features. So x bar is a vector of these features, and it has d minus 1 dimension. As we saw in this California housing data set, there are 8 features. So d minus 1 is equal to 8. Why am I using this d minus 1 instead of a simple d? This will become clear very shortly. Okay. So in that case, now again, we have some fixed cost, which we denote by theta 0. And then each of the uh, individual feature xi gets some weight denoted by theta I. Okay, so we have theta 0 and then theta 1 to theta d minus 1. These are our parameters, and theta 1 to theta d minus 1 are weighing the corresponding features xi's. Okay, so this is our new model. It contains more features, and we expect it to be more representative, more accurate in some sense. Okay, so let me write this in a sort of weird way, and then we'll eventually see what is the utility of writing it like this. So this exact expression I can write in this form. Okay. So because theta 0 doesn't have any feature getting multiplied to it, so theta 0 gets a 1 coefficient. Everything else, theta 1 gets multiplied by x1, theta d minus 1 gets multiplied by xd minus 1. Okay. So now it will become clear why we chose to like take our feature vector as d minus 1 dimensional, because now we redefine our feature vector and we call this new elongated vector. So this vector, rather than d minus 1 entries, now it has d entries. The first entry is always 1 because we use it to correspond to this theta 0, this fixed cost that we are assuming. Okay. And with this 1, we are redefining our feature vector. And now this thing is d-dimensional, which corresponds nicely to like, we don't want to carry that d minus 1 all around. Similarly, in our parameter, the set of parameters, so earlier we had theta 0 to theta d minus 1. We call this whole vector as the weight vector, and we denote this by theta. So theta bar, again, this is a vector and it is d-dimensional. Okay. So given this new notation, this redefined feature vector, which we denote by x bar, and this new weight vector, which we denote by theta bar, we can define our new model as this inner product, theta transpose x bar. Okay, so this is our model for predicting the house of the price of a house. So given the feature vector corresponding to a house, let us denote it by x bar. And given our set of parameters, which will weigh different features differently, we denoted by theta bar, our model for predicting the value of a house is we just take the inner product of the parameters with the feature vector. Okay. So this is exactly what I've said. Given a new house with a feature vector x0 bar, my model, which I denote by f of theta, it has weights theta and it will predict the cost of this new house with feature vector x0 bar by this. Okay. Okay, but then the question is like, how do I build this model, or like, how do I find the weights? So essentially, my model, this f of theta, this is nothing. So this f of theta is nothing. It is just parameterized by my vector theta. So how do I find these weights? Okay. So any questions so far? Uh, I see. So you want me to use laser pointer? Let me see. Does this work? Okay, sure. I will use this laser pointer going forward. Okay, so then the question is that how do we build this model? How do we find the correct weights for our model? That's a big question. And a simple way, and as you many of you would have guessed, is that given some set of features like corresponding to different houses, I have different features. So in the California data set, I have average prices for 20,000 blocks. So I can think of there being 20,000 feature vectors corresponding to 20,000 so-called average houses. In that case, I can use these to train my model. Okay, so we'll get to what exactly this training the model means in some time. But intuitively, like this is what we are going to do, that given some feature vectors and the cost corresponding to the houses that own these feature vectors, we can use this data to train our model. This is basically what happens in supervised learning. Okay, so given this pairs of feature vectors xn and the houses. So let me delete this. Yeah. So given xn's, which are the features for house n, and yn, which is the cost of the house, the nth house, I have capital N such pairs. So capital N is the number of houses for which I have the data, or it is my number of training samples. Using this data set, I want to train my model f theta. Okay. And my goal is that at least on these houses, which I have in my data set, the prediction of my model, let us denoted by f theta of xn bar. So corresponding to the feature vector for the nth house, my prediction, the prediction of my model should be close to the actual value of that house. Okay. And I want this for most of the houses in this data set. So this is crucial. So let me repeat what I just said. Given I have a data set of some number of houses, or I have data set for some points, what I want is that given the feature vector of each of these points, I want the prediction of my model to be close to what the actual value, or what the label in case of classification, or what the value yn in case of regression is for most of these houses. I might not be able to ensure that for all the houses, but I want it to be true for most of the houses. Okay. So in that case, I have a few questions that I need to answer. So first is that how do I measure that the the value predicted by my model is close to the actual value of the house? How do I measure that thing? Right? And the second thing is that how do I ensure that this this property, that f theta of xn is close to yn, this holds for most of the houses? Like it might be possible to it might be possible to ensure this for a lot of houses, but maybe not most of the houses. It is certainly possible to ensure that this holds for just one house. I can like just make my model spit out yn because that is part of the training data. But I want to ensure that this happens for most of the houses. So how do I do that? So there are two questions to answer here. First is, how do I ensure that the output of my model is close to the actual value corresponding to this feature? And the second thing is, how do I ensure that this closeness holds for most of the houses? Okay. So one of the simplest choices to ensure that is given by a simple uh, squared loss. So here, what I do is I take for each house X with features Xn, I take the prediction of my model. I look at its difference from the actual value and I square it. Then I take the average of this squared difference over all the houses. Okay. So I have a 1 over n, then I have a summation over n, and I'm looking at the squared difference. This 1 over 2 is here for a very specific reason, which will become clear in due course. But for now, just ignore it. Okay. Yeah, this is the mean squared error. Okay, so now I have a question for you. What other choices? So this is sort of like a homework for you to think about. What other choices can you think of? Like what other choices can you come up with which will ensure that f theta of xn is close to yn? So instead of this squared error, what other choices you can think of? And what other choices can you think of which ensure this for most of the houses rather than simple average? What else can I do? Okay, so think about this, and these give rise to a number of loss functions that we encounter in machine learning. Okay. Okay, so this is, and recall that I explicitly chose my model to be. So I explicitly chose that given feature vector x, my model gives the output theta transpose x. That was what I had decided. So plugging that inside this expression, I get this thing. Okay. Now let me write it more explicitly, and that would give me a compact notation for this loss function. Okay. So first, let us write this difference between the mean absolute error r squared. Yeah. Yeah. Abdullah, Ikram, yeah, all of these choices make sense. Now, I think the more interesting question is how will they impact the eventual model? So, like, I encourage all of you to think about how these different choices will impact the eventual model. Okay, so now that we have like these squared differences, now let us like collect all these differences and collect them into a vector. So for the first house, we have y1 minus x1 transpose theta. For the second house, we have y2 minus x2 transpose theta, and so on. For the nth house, we have yn minus xn transpose theta. Okay. So I will now split this difference into a vector which just contains all the y entries. So yn to y1 to y capital N. And then I once again split this vector which contains these x1 transpose theta, x2 transpose theta, and so on. So what I do is, because theta is present in all of them, I take theta outside. This is a vector. And then I look at what else is remaining. So in the first, I have this x1 transpose. Okay. So this becomes a row vector. Then I have x2 transpose, again, a row vector. I have xn transpose, again, a row vector. So this sort of becomes a matrix which has capital N number of rows, right? And then theta is a vector which has how many entries? This has d entries. Okay, because I decided that my feature vector is d-dimensional and uh, my parameter vector is also d-dimensional. Okay, so this means that this new notation, so I collected all the y's and let me denote it by a y vector because there are n values corresponding to n houses. So this is an n cross 1. So this is an n dimensional vector. Theta is clearly a d-dimensional vector, so I've written it d cross 1. And this matrix, this contains n rows corresponding to the n houses. So there are n rows, and then each of the row has d entries, which are the d features. So this is an n cross d dimensional matrix. So let us denote it by capital X. Uh, so for some time, I will keep this notation of a bold X to denote that this capital and bold means it's a matrix, but I will not carry it consistently. Okay, so for the first few instances, I will keep this bold capital X, but I won't be consistent going forward. Okay, so in that case, we can write like this loss function using this notation. Okay. So I want you to take a minute and express this loss function, this specific loss function using these vectors y and theta and this matrix X. So like take a minute to write this down. Yeah, I will be sharing these notes. Uh, Yeah, also so I'm purposefully going a little slow. If you feel that I'm going too fast, then feel free to ask questions. And I would also encourage you to like answer each other's questions in the chat. Also, if you feel like I'm going too slow, feel free to ask like more advanced questions. So in like you would notice that I have a right like almost the right one third of the page I've separated by a line. So I've added a little more details in that. Also, I have given like few pointers to a little slightly more advanced things there also. So if you have slightly more advanced questions, feel free to ask them, and I would be happy to address them like either in the break, or if it's a short question, I would answer it right away. There is one question: how did you expand the previous function into this more explicit form? Uh, I'm not sure what you mean. So do you mean this explicit form? So we assume this specific form for our model, and that's why we could substitute this theta transpose x into here, and that's how we get this. Okay, so let us continue now. And the question I had was that using this notation of these vectors y, theta, and the matrix x, how can we write this specific loss function, which is a summation over n houses into uh, in the form of vectors? Okay, so I hope some of you have done that already. If not, let's see. So I would encourage, if you don't see how this happened, then I would encourage you to like work it out explicitly in your own time. But essentially, uh, this this loss function, so maybe let me write it in red. You can explicitly write this as y minus x theta transpose y minus x theta. And then we have a 2 and an n in the denominator. Okay. So I would encourage you to expand this out. So this is y is a vector, x is a matrix, theta is a vector. I would encourage you to expand it out explicitly to see that this is exactly what we have. Okay. So this is what we get. And I've also given, so there is one more notation I would use, that you can actually write this in this form. Oops, did I? Yeah. Yeah, you can actually write this loss in a very compact form. So notice that we have Y, which is the house prices. We have X, the matrix of features for each house, theta, the parameter vector. You multiply X by theta, and you will get an n-dimensional vector. And you just look at the difference of these two n-dimensional vectors, and you look at their L2 norm and square it. So L2 norm, for those of you, uh, second multiplier should also have y bar. How the y minus theta x change to y minus x transpose theta? So I would encourage all of you to take a few minutes to do this computation explicitly, and you would see that this is true. So a little clarification. If your question is how did theta transpose x becomes x times theta, so then note that xn transpose theta is the same as theta transpose xn. So using this, you can come up with it. Okay, so this thing should be straightforward coming from this explanation. And how do we get from this to this? Comes from this explanation. So for any p-dimensional vector, where p can be any positive integer, you can always write the L2 norm square as x transpose x. So L2 norm square of x is x transpose x, which in turn is the summation of the square of all the entries. Okay. So we are essentially looking at the length of the vector in the Euclidean length of the vector and squaring it. Okay. So that's how we get this notation. Okay. So great. So now recall that the question that we had was that how do we measure that our model is doing well? How do we measure that on each house our model is actually predicting the price of the house well? And then how do we also do that for most of the houses? And what we did was we averaged over all the houses and we looked at the difference between the model's prediction and so maybe I should write it down. So we looked at average over all the houses. And then we looked at the prediction of the model, which was f of theta of xn. And what was the actual price of the house, which was yn. And we squared it. And there was also a 1 over 2. Okay. And in a much more compact notation, this thing turns out to be this difference of vectors and then L2 norm square of it. Okay. So now we have a loss function. We have a loss. We have a loss in terms of the weight vector theta. Okay. We know y, the cost of all the houses. We know x, the features corresponding to all the houses. All we need is the theta bar, which will sort of ensure that this loss is as small as possible. Okay. If this loss is as small as possible, that would ensure that on most of the houses, the prediction of my model is close to the actual price of the house. Right? Okay. So that's exactly what I have written. Now that we have an objective or a loss function. So this thing is called a loss function. This is also called an objective function. And in order to ensure that our model is doing well, we want to minimize this loss. Okay. And this can very easily be written in the following way. So we want to minimize this loss. This loss is exactly what we had here. And we want to minimize it over theta because theta is the only unknown. Theta is what we choose uh, in our model. Okay. We get to decide what theta is. So we want to find what the best theta is. So that's a very good question about argument. I'll come to that in just 1 minute. Okay. Now, the point is that usually I'm not really interested in finding what the minimum value of this loss function is. Okay. Because even if I find the minimum value, that is not much utility to me because I already have the actual prices for the houses I'm looking at. What I'm actually interested in is, if I get a new set of houses, how will I predict the values of those houses? Okay, so I'm actually interested in what minimizes this loss function, not the minimum value per se. I'm more interested in prediction. Okay, so therefore, as Ikram very correctly pointed out, we are interested in the minimizer. Okay, and let us denote this minimizer by theta hat. So we want the model. We don't really care what uh, okay, we do care, but we are not, we don't want to know the value of this loss function. We want to know what minimizes this loss function so that we can do predictions on new houses that we get to see later. Okay, so instead of minimize, we will instead look at argmin. Okay, so I want you to compare these two expressions. So look at this first expression and then look at this second expression. Okay, and I want you to take 30 seconds and tell me what are the differences you see between these two expressions. I want you to list out as many differences as you can. And yeah, tell me in the chat. Right. So Ikram is correct. There is an argmin instead of a minimize. And then Abhishek Suman is also correct that I have removed this n, which is the number of samples, because this, like the value of theta, which minimizes this, would be independent of n. Anything else that you see? Or anything interesting in the second expression other than these two things? Right. We are trying to find the minimizer theta hat. Anything else that you see? Okay, let's find out. So two of the things you guys already pointed out, uh, which are that we have an argmin because we are looking for the minimizer. We got rid of 1 over n because that won't affect the value of the minimizer. Also note that there is this sign here. There is a belongs to sign here. Okay. So instead of an equal to, we have a belongs to. Why does that appear? Right. So as Utkarsh pointed out, the minimum value might be unique and it will be unique, but the minimizer, the value of theta, which achieves this minimum value, this need not be unique. Okay. So the minimizer need not be unique. So that's why we have this argmin might be a set, and we are looking for a, a model theta hat inside this set. Okay. Okay. So now the question is, how do we solve this? Okay. So let's look at first look at a very simple idea, and then we will see how to like what are the drawbacks of that idea, and that will motivate what comes next. Okay, so the first idea is that we have d weights. So does this different theta mean we have different trained model? So think of theta as a generic variable, and we are looking at the minimizer, which we denote by theta hat. Okay, so theta is a variable in terms of which this loss function L is evaluated, and then we are looking at the minimizer, which we choose to denote by theta hat. Okay. So first is very simple idea. Let's do trial and error. We have D weights, and let's try to tune each of these weights and see what changes. So we look at theta 1. uh, we either increase it or decrease it, see how the loss changes. We do that the same for theta 2 and so on. Okay. So that's pretty much how we played with the radio. So I don't know if many of you have seen that radio with a lot of knobs, but you might have seen something like this if you were in electrical engineering and you have seen oscilloscopes in your labs. Okay. So this is one option, that we try to tune each of these thetas by hand, that we increase theta 1, decrease theta 1, and see uh, what happens, and so on. We do it for all the d thetas. Can you think of a problem with this approach? Right. So it is very time consuming, as Rahul pointed out. So let's see. So our housing data set, so D is 9. For 9, if you have 9 knobs on your device, like, you are supposed to find the right like how much to turn each of those 9 knobs so that you end up with the, like, whatever the correct setting is. So this is quite a nuisance. Okay. But California housing data set is unique in the sense that it only has 8 features. Okay. But house prices can depend on a lot more things, right? They need not depend on just 8 things. And I'm not just making this thing up. There is something called the Ames housing data set. I think this is from Ames, Iowa. And this housing data set contains 81 features. Okay. So instead of just 8 features, now there are 81 features for each house. And as you can imagine, if you think tuning 9 knobs was difficult, tuning 81 or 82 knobs is going to be a lot more challenging. Okay. But what about if we go beyond housing data sets? If we look at large data sets, if you go to uh, modern ML models, because we want to find something which is scalable to, like, very large data sets and very large models. And let's see what happens in that case. So this is a plot of what is the scale of models, ML models, as time progressed. And this is slightly dated because, as you can see, it ends in 2022. But already back then, the number of parameters had reached around 10 to the 13, which is like a lot. It's, yeah, this is 10,000 billion. Yeah, so a billion is 10 to the 9. So this is like 10 trillion kind of a model. Clearly, you are not going to tune these by hand just by changing one, uh, increasing one, then decreasing it and finding out what happens. Okay. So we need a principled approach. This is not scalable, as a lot of you have pointed out. Okay. So trial and error is not scalable. Uh, what is another approach? Another approach is what we, like, saw in our high school, or I think 11th or 12th, which was take derivative and set it to 0. Okay. So this is what we have done for a very long time, that take derivative and set to 0. So we will look at this in some detail and then realize what the drawback of this approach is. But this will, like, give us a lot of insights into what will come after this. Okay. So take derivative and set to 0 when we have functions which depend on multiple variables. So derivatives exist for one-dimensional function, right? So functions of scalars. But in this case, because our loss function depends on theta, and theta is d-dimensional, so we have to look at something called the gradient. Okay. So let's compute the gradient and set it to 0. So what is the gradient? If you have not seen this before, then gradient is essentially a vector which contains partial derivatives with respect to all the parameters. Okay. So here I'm computing gradient with respect to theta. Theta is d-dimensional. It has d components, theta 1, theta 2, and so on till theta d, I will compute partial derivatives of the loss with respect to all these d parameters. So this is the partial with respect to theta 1, this is the partial with respect to theta 2, and so on. This is the partial with respect to theta d. And therefore, naturally, this is a d-dimensional vector. Okay. So I will compute this gradient and I will set it to 0. And then I will try to find a point. Again, let me denote it by theta hat. So this theta hat is consistent with what we denoted the minimizer earlier, because we hope this will give us the minimizer. We are not certain, but we hope that this will give us the minimizer. So we are looking for a theta hat at such that at this point, so at theta equal to theta hat, this gradient would be 0. And gradient being 0, because gradient is a vector, so this 0 is actually a 0 vector which contains all 0 entries. So it is a d-dimensional vector in which all the d entries are 0. Okay. Okay. So now we have we have some idea what we should do. So simple try and error won't work. So we can compute the gradient of this loss function with respect to this theta, set it to 0. But for that, we will first need to compute the gradient of this loss. So let us compute the gradient. So this is our loss. This is the compact norm-based notation, and this is the average over the n houses and square of the difference, that notation. And first, I will briefly show you how to compute the gradient uh, component by component, and then we will go to vector calculus. Okay. So if you try to compute the partial derivative of this loss with respect to theta hat, you will get something like this. So here, what I'm trying to do is, because I have to compute the, let me change the color, maybe this helps. So I'm trying to compute the partial with respect to theta I. So I will isolate theta I in this expression. So I can write this thing as yn, and then I've split the inner product into a summation which does not contain theta I and the term which contains theta I. Okay. And then I differentiate it using chain rule. So I will end up with something like this. This is just the partial with respect to theta I. Now I have to repeat the same process for all I equal to 1 to d. So this is clearly cumbersome. We need a more compact notation and we need to use some vector calculus. Okay. So if you know vector calculus, this would be a recap for you. If you don't, then this will be quite useful for you. So this is a small detour we will take. I will just give you two expressions and that's all. I will not give you anything more. I will give you only what we need. Okay. So we will look at two kinds of functions. One is a function of this form. So given that I want to compute the gradient with respect to W vector, and W is some p-dimensional vector. So I'm using different values here. I'm not using d-dimensional vectors. I'm not using theta because I want to convey to you what the general idea is. Okay. So I have a function of W vector. I have an inner product and I want to compute the gradient of this inner product with respect to W. And W is a p-dimensional vector. So I have written this explicitly. So I have the partial with respect to W1, I have the partial with respect to W2, and so on. I have the partial with respect to WP. So this is clearly a p-dimensional vector. And if you go over this entire computation, and I encourage you to go over it once. So you need to do it once in your life, and then you will remember it forever. If you do it once, then you will realize the expression is just the A vector. Okay. Because A is also a p-dimensional vector, and that's exactly what the gradient of this inner product is. Okay. So this is something we will use time and again. And the second thing is, given a symmetric P cross P matrix, So I will try to like mention this result wherever I use it, but it is always good to remember this. Second, given a symmetric P cross P matrix C, suppose I compute the gradient of this function. So I have a quadratic function. I mean, it is quadratic in W. This is W transpose C times W. W is also a p-dimensional vector. C is a P cross P symmetric matrix. In that case, if you look at the gradient of this quadratic function, quadratic in W, then this is exactly this. Okay. So these are the two results from vector calculus that I want you to remember. And just for like so that you remember, it's easy for you to remember. Note that this is simple generalization of if you try to differentiate this function where x is a scalar, a is a scalar, then this is simply a. And this result is a generalization of this. Okay. Similarly, the second result is a generalization of this. If you have a times x square, if you have a quadratic function, uh, you can, if you differentiate it, you will simply get 2 times a times x. I should have used c here just for the sake of consistency. So you get 2 times c times x. Okay. So that's exactly what I'm generalizing here. So this result generalizes this, and this result generalizes this. This seems to be multivariate normal distribution. I'm not sure what you mean by multivariate normal here. We are not talking about any distributions. We are just talking about like uh, vector calculus. I mean, this is certainly useful in multivariate normal distribution when you manipulate them. But here we are only talking about vector calculus. Okay. So I have written these results here as well, and now we will use them. Okay. So going forward, I will not repeat this cumbersome notation with the summation. I will only work with this. Oops. I will only, what is happening? I will only work with this norm square notation. Okay. So now we have to differentiate. Uh, is it possible to show the derivation of the second formula? Uh, I will not show you the derivation, but essentially, if C is not symmetric, in that case, so this is essentially like, I mean, it's a chain rule kind of thing. So first you differentiate this, keeping this same, and then you keep this fixed and differentiate this. So you will end up with two terms. Okay. If C was not symmetric, you will end up with something like this, C plus C transpose W. But because C is symmetric, so you get 2 times C. So use that, uh, basically use this f of x times g of x, the derivative of product, and you will get this. Okay. Okay, good. Uh, so as I said, now we will only be working with this norm square notation, and I want you guys to take 1 minute and find the gradient of this loss function using these two rules and type in the expression in the chat. So I think I should give you one more uh, result to help with this computation. So you might also want to use that if you have a norm square, this can be expressed as x transpose x. So you might need this as well. Okay, so let's see. Uh, let's see. I think Venkat got it right. Yeah. So let's see. So when differentiating, like when computing gradients, I think it's in addition to these rules, it is also helpful if you are a little mindful of the dimensions your output should be. So if theta is a d-dimensional vector, then the gradient has to be dimensional. It should be a vector, or sort of, it has to be a d cross 1 matrix. Okay. So let's see. So first, we have this norm square. So we can expand it using this result, and we can expand it in the following form. Okay. So I want you to verify that this is exactly what you get. So why we can leave it alone, because this does not depend on theta. Then we have cross terms. So we will get two cross terms and we can write it in this form. And this x theta norm square, using again this result, we can write it in this form. Okay. So the first term is independent of theta. If we differentiate it with respect to theta, we get a zero. Remember that this is a zero vector. This is not a scalar zero. Okay, so maybe I should put a bar on top of it. Then this is a linear function with theta, and using this result, we end up with this as its gradient. And similarly, this is a quadratic function in theta. Using this result, we end up with this as its gradient. And here we have used that x transpose x is a symmetric function. Okay, you take its transpose, you get back the same thing. Okay, so here we have used the fact that x transpose x is symmetric. So note that, like, we are using a number of things in this simple computation. We began with this to expand this term, and then we broke it into three terms. So we would get four terms, but two terms will be identically this. So we combine them. We get three terms. One of them is completely independent of theta. The other is a linear function in theta. So we can use this rule. And the third one is quadratic in theta. We can use this rule, but we have to be mindful that the matrix sitting in the quadratic function is a symmetric matrix. Okay. So after doing all this, we end up with this thing. And now, finally, the 1 over 2 that we had been carrying, oops, for some reason I keep selecting the eraser with my pencil. Okay. So the 1 over 2 which we had been carrying for so long, now we see the reason why we were carrying this, because when you differentiate a squared function, when you differentiate a square, you get a 2, and that's why we have a 2 here, we have a 2 here, and these 2's get cancelled with 1 over 2. So that was the reason we were working with this 1 over 2 all along. And this is eventually our gradient. As Venkat correctly pointed out, I think Purvi Deshpande also pointed that out. uh, right, with the sign flipped. Okay, so now we have the gradient, and we began with the idea that we will find the gradient, we will set it to 0 and find a theta which satisfies that. Okay, so let's see. So if we look at this gradient and set it to 0, we end up with this expression. Okay, and these expressions are like, this kind of expression has its own name in linear regression. It is called a normal equation. Okay, and here note that x, so maybe let me correct this. So x is a capital N cross D matrix. So x transpose x is D cross D matrix. Okay, and if we assume, oops, I think I made this notational error multiple places. So if capital N is greater than D, in that case, so if capital N is greater than D, then X transpose X is, since it is a D cross D matrix, there is some hope that this will be an invertible matrix. If N was smaller than D, then there won't have been any hope that this would be an invertible matrix. Note that this is a big simplification we are making. We are currently in like classical linear regression regime. In deep learning, if you uh, if you have noticed, the number of parameters is usually much, much higher than the number of samples. So whatever we are going to discuss shortly in terms of linear regression is not applicable in the deep learning regime, because there D is always larger than N. Okay. So one question I have is that like, so we will look at the theta hat which satisfies this expression. Okay. So if you look at this theta hat, is this going to be a minimizer, or is it going to be a maximizer, or is it going to be a saddle point? Because just assuming, like just putting gradient equal to 0 does not ensure minimizer. It can be a minimizer or a maximizer or a saddle point. So how do we know which one it would be? Okay, so Ikram says it would be a minimizer. Uh, can it be a maximizer? Okay, so Rahul says it's a convex function, so this will be a minimizer. Abhishek says next derivative. Ikram says depends on objective. Uh, Het Mevada says it may be maximizer or saddle point. Okay. Levi says Hessian is positive semi-definite. Okay, so we'll get to all of this in due course. Okay. So first, let's look at what the solution is. Okay, and we will look at several properties of the solution. We will look at what we need to do to arrive at that solution, and then that will govern where we go next. Okay. Okay, so let's suppose that this X transpose X matrix is invertible. Okay, and we can do that because we have assumed that N is greater than D. If N was smaller than D, this would not be true, because this would be a X transpose X, in that case would be a rank deficient matrix. This will only hold when N is greater than D. Okay. So from normal equations, we can get this expression. Okay. And I have this theta hat LMS. LMS is least mean squared error. So this is sort of the minimizer of this error. Okay. So in order for this matrix to be invertible, I would want that all the columns of X are linearly independent. Okay. So I will not explain this statement. I assume you have some background in linear algebra. So I will not explain this statement much, but this invertibility, uh, yes, rank deficient means determinant is 0, but I would think of it in terms of rank and not in determinant. Determinant is sort of a consequence of that. Okay. So yeah, so X transpose X would be invertible if all columns of X are linearly independent. What that means is each column of X is conveying some information about a feature. Okay, so it can be income, it can be number of bedrooms, it can be location, etc. But linear independence across all those columns means that each feature conveys some unique information about the house price. If the columns were linearly dependent, that would mean that at least one column can be expressed as a linear combination of the other columns. Okay, that intuitively means that there is at least one column or at least one feature which is not conveying any unique information. Okay, the unique information might not be significant, but it is nevertheless some unique information about the house price. Okay. However, in general, this X transpose X is not going to be invertible. In that case, this theta hat will not be unique. It will belong to a set of infinitely many solutions. Okay. So let us denote by theta, capital theta solution as this set of theta, which satisfies this equality, this normal equation. In that case, any element of this set can be expressed in the following form. So any element of this set can be expressed as a combination of two quantities. First is this pseudo inverse of x times y. Here, this is the Moore-Penrose pseudo inverse. Again, this is sort of like this is a generalization of matrix inverse, which holds even for non-invertible matrices. So matrix inverse only exists for invertible matrices. If your matrix is not invertible, you can compute something called a pseudo inverse or a Moore-Penrose pseudo inverse. Okay, so I would encourage you to look it up if you are not familiar. This is not the point of this course, so I will not go into any more detail. In addition to the first term, you will also get some C, and this is any element of the null space of X. Okay, so null space of X, as you recall, is any element. So C belongs to null space of X means that X times C equal to 0. Okay. So if you look at like if you substitute this thing, this expression into this equality, this C would get multiplied with this X and give you 0, and you will only be left with this thing. Okay. So this null space is sort of, because if you recall like the theorems of linear algebra, then this null space is going to be orthogonal to this X. Okay. It's X times X transpose equal to 1 in this equation. I don't understand which equation you mean, but here essentially we are saying that there are infinitely many solutions if X transpose X is not invertible, and each of these solutions takes this form. Okay, but for simplicity, we will only like in our discussion for the next few minutes, we will assume that this X transpose X is invertible. So we have this unique solution for theta, which is given by this thing. Okay. In that case, you can, like, whatever we are going to discuss next, you can do the same exercise for this general case also, but I would leave that to you to do in your own time. But the question I have is that, sure, we can compute this expression for theta hat, which minimizes that loss function. So recall that the loss function was y minus x times theta norm square half. This was my L theta. So theta hat is minimizing this thing, and it has this closed form. Oops, once again, I selected. Yeah, it has this closed form. But the question I have is that how many computations does this computing this closed form solution require? Like how many computations, how many basic mathematical computations I need to do to compute this theta hat LMS, given I have the matrix X and the vector Y. Okay, so let's see. So in order to compute this closed form expression, I would first need to compute this D cross D matrix. Then I would need to invert it. I would need to compute this matrix vector multiplication. and then I would need to multiply the resulting vector with this matrix inverse. Okay. So in theta hat normal equation, we have got y and x and y hat same. How could this provide difference vectors of theta values? I'm not sure I followed the question. Can you unmute yourself and ask this question?
Yeah, sure. So my question is, as we said that we can have different values of theta, which will minimize our function, right? Loss function. Now,
Right.
if we see this normal equation, we have got the x transpose x inverse x transpose y hat, right? All of these
Right.
are same, right? For a training sample, right? All of these are same. How could
Okay.
this multiplication will result in a different set of theta hat values?
No. So this is a unique solution. Like if x is invertible, then this is a unique vector you would get. Like there is no ambiguity and there are no multiple solutions. Multiple solutions exist only when x transpose x is not invertible.
Okay, got it. Thank you.
Yeah. Okay, so as I was saying, this is the solution we want to compute, and there are multiple steps involved in computing this solution. So let's see what those multiple steps are. First, we need to compute this D cross D matrix X transpose X. Okay, and let's write them explicitly. So this is our matrix X, and if we write the X transpose and X explicitly, then you can see that this X transpose X multiplication essentially gives you this matrix. Okay, it's a summation of matrices of the form xi transpose, which are like rank 1 matrices. So uh, so I will first describe all the steps, and then I will ask you to think of what the underlying computation cost of each of these steps is. Okay, so this is what we get when we try to do this X transpose X. Then when we multiply X transpose Y, so we are multiplying a D cross N matrix X transpose with an n dimensional vector. Okay, so what is the computation cost of this multiplication? And finally, we have to invert this D cross D matrix and multiply it with a D dimensional vector. So we have to multiply a D cross D matrix after inverting to a D dimensional vector. So what is the cost of this step? So we have three steps here. I want you to take 1 minute and find out what the cost of each of these three steps is in terms of N and D. Okay, we have one answer from Ahish. So let's wait for a couple more answers and then we'll. Okay, so there is ND square is the first computation. Okay, so let's begin with that. I hope ND square is first, ND is second, right? How about the third one? Assuming N is much lower, more than D, the computation is sure. How about the third one? Okay, so let's see. Okay, so as we saw, like this X transpose X is a D cross D matrix, and it can be seen as a summation of n rank 1 matrices. So this Xi transpose is a D cross D matrix, which is rank 1. So to form each of these matrix, oops. So to form each of these matrix, we would require D square computation. There are n such matrices, so we require n times D square computation. So a lot of you answered that correctly. Abhishek, Venkat, uh, let me know if there are some questions around this. Then to compute X transpose Y, this is a D cross N matrix with and you are multiplying it with an n-dimensional vector. Whenever you have a matrix vector multiplication, you look at what is the number of entries in the matrix, and so this is an order n times D computation. And finally, because we have a matrix inversion, so in the worst case, using crude algorithms, this is a D cube computation. Once we have this D cross D matrix, we are multiplying it with another D cross 1 vector. So the matrix vector multiplication is order D square. So the overall computation is order D cube. Okay. So the total computation is order ND square plus order ND plus order D cube. So because this would be much smaller compared to this, the overall complexity is order ND square plus order D cube. And as Nisarg pointed out, if n is much, much larger than D, yes. So for the third one, let me explain that again. So we have a D cross D matrix, X transpose X. This is D cross D. To invert it, in matrix inversion is using very crude algorithms, an order D cube operation. Okay. So like this is from very, if you look at how matrices are inverted in your like school textbooks, basically you compute the adjoint, determinant, etc. In that case, that's an order D cube operation. Like I would encourage you to like go over that computation again and look into it. But in the worst case, it's order D cube. There are like fancy algorithms to do faster matrix computation. I think the state of the art is 2.4 something or 2.3 something. This is an active area of research. Uh, Actually, I think a few years ago, AI was able to, using reinforcement learning, was able to come up with a matrix multiplication algorithm, which was like faster than the fastest known. Okay, but in the worst case, we can assume this is order D cube. Uh, and then we have a D cross D matrix, which is X transpose X inverse. This is again a D cross D matrix, D cross D. And we are multiplying a D, so this is a D cross 1 vector. We are multiplying a D cross D matrix with a D cross 1 vector. So we have order D square complexity. So this is the complexity of the third part. The question, and then we have three terms, order ND square, order ND, and order D cube. Now clearly this is much smaller than this. Okay. So the first two contribute complexity of order ND square, and this comes from step 3. Okay. Now let's look at some very basic numbers. So suppose both of them are roughly of the order of 10 to the 5. Okay. N is larger than D, but they are both of the same order. In that case, this is like 10 to the 15 computation. Okay. And 10 to the 5 is not that big of a problem. Like essentially, you are looking at 1 lakh samples and 1 lakh features, or 1 lakh, like a model with 1 lakh parameters. This is not a very big model. And already you have like, you have reached a complexity which you are not going to achieve. You are not going to solve this problem on your laptop in any reasonable amount of time. Okay. And this is like a medium-sized problem. So we need something better, we need something faster. Okay. So that basically brings us to like what the point of this entire course is. So we spent almost the first 80 minutes getting there, but now we have a very good reason, motivated by a very good application of linear regression to get there. Okay, so I will begin gradient descent, and I will try to go for about 5 to 10 minutes, and then we will stop. Okay, so anyone know who this mathematician is? So I've told you this is a mathematician. This is one of the most famous mathematicians of all time. Any guesses on who this is? Oh, I gave away the name. Okay, anyways, so this is French mathematician Augustin Louis Cauchy. He lived in early 18th century. So interestingly, I think Cauchy has the most number of things named after him in math. Like just in elasticity, I was reading on his wiki page, there are about 16 things in elasticity that are named after him. So, uh, so this was proposed by Cauchy in 19th century. I'm pretty sure people before him would also have worked with some variants of it. But it turns out that Cauchy wrote the following in his notes, that recall the R.D. Sharma textbook from class 11th and 12th and just use derivatives. Okay, so this is an actual quote from Cauchy. So what he suggested was that given a loss function g, if you want to minimize this, and this loss function depends on some parameter w, then you do the following. You start from where you are. So suppose w is where you are, w is the value of the parameter where you are, and you compute the derivative of this loss function at w, and then you take a step in the direction of the negative derivative. So you start at w, you go in the negative g prime direction, and your progress is going to be mediated or amplified by this step size eta. So eta is a step size. In ML, this is also called the learning rate. And g prime is the derivative of the loss function g at w. Okay, so he gave this very simple idea. Okay. And in multiple dimensions, as you can imagine, we are going to work with gradients rather than derivatives. Okay, so suppose you are at some parameter or weight vector theta, then using step size eta, you move in the direction of the negative gradient. And that's how you minimize your loss L. Okay, and writing it out more explicitly. So suppose this is your current weight vector, theta 1 to theta t. And then, as we have seen already, gradient is just a vector which contains all the partial derivatives of surprise Cauchy. Yeah. Cauchy was also a fan of R.D. Sharma, it turns out. Okay, so for each component of the parameter vector, how you update it is you take the partial with respect to this parameter. So for theta 1, you take a partial with respect to theta 1. For theta 2, you take a partial with respect to theta 2, and so on. For theta d, you take a partial with respect to theta d, and that's how you update your parameter vector. Okay. So now the question is, why does this make sense? Like, why is it an intelligent thing to do? So think about it for 30 seconds and tell me, why is moving in the direction of negative derivative, as Cauchy said, or moving in the direction of negative gradient is a sensible thing to do? So take 30 seconds. In the meantime, let me see how far we can go. Right. So as Ahish said, that gradient gives the direction of steepest increase. So negative gradient gives the direction of steepest decrease. So that's exactly correct. So it turns out that gradient gives the direction of quickest change or steepest change in the function. So at any point, if you look at the direction of the gradient, that is the direction in which if you take a small step, you will increase the function value by the largest amount. So let's see that through an example. Okay. So suppose this is our loss function. This is a function which is of two variables, x and y, and it is quadratic in both x and y. A is some positive constant, B is another constant. If you look at the gradient of this function at any point x, y, this is what it looks like, right? So this is quite straightforward. Let us plot this function and see what it looks like. Okay. So this red surface, so here below this grid is the XY plane. And if we plot the function value on the Z axis, then we get something, this bowl shaped figure is what we get. So this is like a parabola rotated along the around the Y axis. Okay. So this is the value of the function. And if we plot this gradient on the XY plane, then we get these weird looking circles and arrows. So let's look at what is happening here. At any point x comma y, the gradient is, yeah. So if you are in this, this positive orthant, where both x and y are positive, then at any point, the gradient is pointing outwards, right? Similarly, here the gradient is pointing outwards. Everywhere the gradient is pointing outwards. Okay. So if x is negative, it is becoming more negative. If it is positive, it is becoming more positive. Okay. Suppose maybe you might want to take a bowl in your hand to visualize this clearly. But suppose you are at any point on the surface of this bowl. Okay. You try to increase the value of the function. So basically, you are trying to climb up the bowl. You are trying to go up the bowl. Now, it turns out that the way to increase the function value the fastest, or the way to climb up the bowl the fastest, is to actually go in the direction of the gradient. Okay. So if you take a very small step in the direction of the gradient, if you take an infinitesimally small step in the direction of the gradient, that is the direction of the steepest change in the function value. This is a property of the gradient. And that is why taking a negative gradient step makes sense if you are trying to minimize a function. Okay. So just to state that again, since gradient gives the direction of quickest change in x, so to minimize L, move in the opposite direction. Okay. And therefore, we end up with the first algorithm of this course, which is the famous gradient descent algorithm. Suppose you have a loss function L. Now, our loss function L need not be the mean squared error of linear regression. It can be any loss function. So we want to minimize the loss L, which is a function of theta. To do that, we run the following algorithm. We initialize our model at some point. So in this course, we won't worry about initialization at all. There is a lot of work on how you should initialize as well. We won't worry about that. And then after this initialization, you run this for loop. So you run this for either a predefined number of iterations, capital T, or you run it until convergence, whichever comes first. Okay. And what you do is in iteration T, your current weight vector is theta T. You compute the gradient of your loss at this point and take a step in the direction of the negative gradient. So just to explain that notation, we are computing this gradient of the loss function at this current point, theta equal to theta T. Okay. And then once we have this gradient vector, we will take a step in the direction of the negative gradient, and this will be amplified by this step size eta. And this is exactly the update written coordinate wise. Okay. So this is our gradient descent algorithm. So this is, I think, a good time to stop. And we will continue in 15 minutes. So that will be 10:50 a.m., right? So we will continue at 10:50 a.m. Yeah, so Ikram, thanks for pointing the initialization techniques. We will not talk about these initialization techniques at all. Okay, so we'll meet in 15 minutes. Thanks. Okay, so let's begin again. So before we begin, uh, let me post a comment in the chat. So I want you guys to give me feedback about like the pace at which we are going. So I will put in three options and I want you to like add your reaction with a thumbs up to whichever of the three you find like best suits you. Okay. So the question is how do you like the pace of instruction? How do you like the pace of the course? So the first option is too fast. The second option is good enough. And the third option is too slow. Okay. So yeah, please like react with a thumbs up to one of these three options. So that will help me tailor the pace going forward. And then we'll begin in 1 minute. No, you can just react to the three options with a thumbs up, whichever of the three you like the most. Okay, so I will post the question and the three options again. So the question is, how do you like the pace of the course? And I will post three options. So first is too slow. Second is so first is too fast. Second is good enough, and third is too slow. So if you can, yeah, instead of typing, like if you can react to the react with a thumbs up to the options, that would help because I cannot count how many people respond to what option. Oh, I see. Let me post the options once again. So the three options are the first is too fast, the second is good enough, and the third is too slow. Yeah, okay. So let's get started. So there are a few of you for whom the pace is too slow. I think the content we cover now you will like better. And again, like I would strongly encourage you to ask if you have some advanced question in whatever I'm covering. And I'll be happy to answer those as well. Okay. Okay. So can learning rate be different for each parameter? Does it make difference? It can absolutely be different for different parameters. There are methods which do that. There are methods which try to vary the learning rate depending on the properties of the gradient, the values of the gradient. So if for some, uh, they can make the learning rate small for components which have very small gradient. Methods like ADAM or ADAGRAD do that. Okay, so once again, this is the gradient descent algorithm, wherein we have to go through. Okay, sure. So let me state those right now. So some of the reference, like the basics, for example, convexity, the Boyd textbook is good. So we'll get to convexity in a few minutes. Uh, then for the gradient descent results, so there is a monograph called Convex Optimization by Sebastian Bubeck. Sebastian Bubeck. This is quite good. Then there is a book called by Ben Recht and Stephen Wright. I think it's called Optimization for Big Data or something like that. I will check the big data. This is good reference as well. I will point out anything else wherever it is needed. Okay, so now that we have seen gradient descent, let's see like if it gives any benefit in terms of linear regression. So the problem we had with uh, accessible book as an alternate to Stephen Boyd, uh, I would say Stephen Boyd is a pretty accessible book. If it seems difficult, then I think you have to just give it some time. Like it's a pretty well written book. Yeah, like try solving as many problems for it as possible. Uh, yeah, without like anything less than Stephen Boyd, I would say is not really sufficient. Okay, so as we discussed that the drawback with linear regression was the huge complexity. So this was the complexity of linear regression. And even though it resulted in a closed form expression, this complexity was excessive. So we want to do something iterative and hopefully get a better complexity. Okay, so let's see what gradient descent does if we try to solve linear regression using gradient descent. So recall that this is the loss function for gradient descent. And as we did this little exercise in the first part, that the gradient of this loss function was given by this expression. So here x transpose x times theta minus x transpose times y. Here x is the matrix which contains all the features for all the, for example, all the features for all the houses in the housing data set, and y contained the costs for different houses. Now we want to understand what is the cost of a single step. So this at the top of your screen is gradient descent. And if we plug in this specific value of the gradient, then we end up with this update, right? So in here, let's call this entire this gradient as delta theta t just for the time being. And let's first find out what is the complexity of computing this update. Okay. So as you can see, this gradient has two components. First, we have to compute this thing, x transpose x times theta t, and then we have to compute this x transpose y. Okay, so first, x transpose x is a d cross d matrix. Theta is a d cross 1 vector. We want to multiply a matrix with a vector. So this will have some cost. Okay, and then, right. And then we have this x transpose y. So x transpose is a d cross n uh, matrix, and we want to multiply an n cross 1 vector with it. So this will result in some cost. So take 30 seconds and tell me what the cost of both of these computations is. This matrix vector multiplication and this matrix vector multiplication. Yeah, please note that we are not inverting any matrix here. We are just multiplying a D cross D matrix with a D cross 1 vector, and we are multiplying a D cross N matrix with an N cross 1 vector. Right. So as Venkat and Abhishek pointed out, the first computation will cost us uh, D. Yeah. So note that like we will first need to compute this X transpose X matrix, and that, as we know from our previous computation, that is a one-time cost of order ND square. Okay. And then we will be multiplying this D cross D with a D cross 1 vector. So this is order D square operation. And similarly, if we do this computation, as Abhishek pointed out, this is an order n times d uh, computation. And finally, once we have all these vectors, so note that this result is a d cross 1 vector, this result is a d cross 1 vector, and we have to do some additions here to finally get theta t plus 1, right? So this final step is an order d uh, addition, right? So we had to do some. So first we had to compute the X transpose X. This is a one-time cost because we do it at the beginning. At each step, we do this matrix vector multiplication, this matrix vector multiplication, and then addition of a few vectors. So the total cost is order D square plus order ND plus order D. So the one-time cost of the algorithm is order ND square, which is required to compute this matrix. And then the running cost that we have to spend at each iteration, that running cost is number of iterations. So this is the total number of iterations that we run times order D square. So the total cost is order T times D square. Here T is the number of iterations that we will run. Okay. So recall that earlier when we were doing a closed form, we had a closed form expression for linear regression. So just to recall, this was X transpose X times inverse times X transpose Y. This was our theta hat. And the cost of computing this turned out to be order ND square plus D cube. On the other hand, now our total cost is order ND square. This is the one-time cost, and the running cost is order T times D square. Okay. So if T is smaller than both D and N, then we are in pretty good shape, because if T is smaller than D, then it will be this term will be smaller than D cube. And if T is smaller than N, then this cost will be smaller than this one-time fixed cost. Okay. So gradient descent would be useful to us if it so happens that the number of iterations that we need to run is smaller than both the dimension of the problem as well as the number of samples that we have. Okay. So our discussion, like a lot of the discussion for the remainder of this course would be focused on finding what this T can be in different situations. Okay. Okay. So now let me if X is a feature, does X transpose signify anything? So as we saw that, so if we go back a few pages, yeah, so X was this matrix, which contains, so each row of it contained the features for a specific house, right? So then X transpose is a D cross N matrix in which like, so each column corresponds to features for a specific house, right? So in X, each row corresponds to features for a house, while in X transpose, each column corresponds to features in the house. So like it's like a straightforward uh, interpretation you can have. Okay, so once we have sort of this broad goal that we want to understand when the number of iterations that gradient descent requires, uh, in running cost, should we have n also? Uh, Not really, because once we compute this matrix X transpose X, like we uh yeah, so X transpose X is a fixed vector, fixed matrix. Similarly, X transpose Y is also a fixed vector. So you need to compute both of these only once. So this is a matrix which you need to compute only once. And sorry, this is a vector you only need to compute only once. So once you have computed this, this cost is never going to be repeated. Okay. So now we are interested in like what this t can be for gradient descent under different conditions. So this brings us to several questions that we aim to answer in this course in the remaining time. So just for reminder, this is our gradient descent algorithm. So we run it for either capital T iterations or until convergence if convergence happens earlier. And the question, like the broadest question we can ask is that does gradient descent converge? Does it even converge? Right? Or will we never converge? And if it converges, the question is when does it converge? It is possible that sometimes it converges, sometimes it doesn't. So then the question is under what conditions it converges? If it converges, the follow-up question should be how quickly does it converge? So this question about what are the criteria for convergence, there are different criteria under different situations, and we'll get to them very shortly. Okay. So how quickly does it converge? So this will of course depend on the criteria that we impose for convergence, but this is also a question that if it converges, how quickly does it converge? And can we do something to make sure that either gradient descent converges quickly, or can we do something to make sure that another algorithm which is faster than gradient descent, which converges even quicker than gradient descent? So it will turn out that the answer to both questions, like does it converge, how fast this converges, can we do something better? This will depend on both the loss function, what are the properties of the loss function, as well as the step size that we choose. Okay. And this is like sort of evident because these two are basically the things that we are working with. Eta is a design parameter, the step size that we choose, and the loss function, we have to depend on the properties of the loss function. So Ikram says convex loss function. So as you will see that just convexity is not sufficient. Newton's method converges fast, but it is expensive. That's true. Also, uh, like the convergence of Newton's method is understood uh, less in fewer settings compared to gradient descent. Okay. The next question is that suppose gradient descent converges, but we know that linear regression gives you this closed form. So if you insist on solving gradient descent in closed form, this is the closed form expression that you get. Are we guaranteed to converge to the same solution if we run gradient descent? So this is another question for us, that are we guaranteed to converge to the solution? And as you can imagine, because linear regression is sort of a special case of a generic loss function L, once we have answered the first two questions, we will have a good understanding of what happens in the specific case of linear regression. Okay. And finally, and this will probably bring us to sometime in the second day, that we saw that the per step cost of gradient descent when we ran it in the context of linear regression was order d square. Okay. So as you can see here, the per iteration, the running cost of gradient descent in every iteration was order d square. Okay. But if you think about it, like if let's say your D is, let's say, a million, or let's say a billion, in that case, order D square is huge. Like this is order 10 to the 12 to 10 to the 18. This is prohibitive cost. We cannot run this on a simple machine. 10 to the 18, like we might not be able to run it except on the most expensive machines in the world, right? So this is huge cost, and we have already seen that models today are much bigger even compared to a million parameters or a billion parameters. Okay, hundreds of billions or even trillions of parameters are common in models these days. So then even order D square computation at every iteration will turn out to be too expensive. So the question is, can we reduce, so this last question, can we reduce the per step cost of gradient descent further? And this will bring us to uh, stochastic gradient descent, which is sort of the workhorse of modern machine learning. Another question is that we saw that our data set contained n samples or n, so n houses, or in general, it had n samples, right? Now, for gradient descent, we said that sure, you can compute this matrix X transpose X and this vector X transpose Y as a one-time cost, and you can store it in your memory, right? But if all these, the data or the features of the n houses or the features of the n samples are distributed across multiple locations, then how do you compute this entire matrix or this entire vector? You might have to collect all the data from multiple locations, but that might be expensive. So how do you do that? And that brings us to distributed SGD or federated learning. Okay, so that will probably be the final thing we discuss tomorrow. Okay, so these are the questions we'll discuss going forward. First, we will be interested exclusively in gradient descent. How does it converge? When does it converge? How quickly it converges? Can we do something even more fancy and get even faster convergence? N- uh, and through the first two questions, you will also get answer to this question about linear regression. That does gradient descent converge to the same solution as we got in the closed form? And finally, we will generalize gradient descent along several axes to get some of the modern ML methods. Okay. So before we get into when does gradient descent converge or if it converges at all, we need to look at certain classes of functions, right? So as Ikram pointed out, convex loss functions. So we certainly will look at convexity, and then we will see that convexity alone is not really sufficient. So we'll need something else. Okay, so for that, we will need to recap convexity a bit. Those of you who took Professor Jayakrishnan Nayar's course on optimization, this will be a recap for you. But I think there is one perspective of convexity which will be new to even people who are familiar with it. And yeah, so Boyd and Vanderberg is a great textbook. It's sort of a Bible of convex optimization. It is freely available. Another resource which I would like to point out is, so there is someone called Ryan Tipshirani. So he's currently at UC Berkeley, but he used to be at CMU till a few years ago. And there he taught a course called convex optimization. He's taught it for several years. So you will find both notes as well as video lectures of this course. And this is one of the, like, I would say it is slightly more advanced compared to Boyd in a few things, but I learned the basics of convex optimization through this course. So I would very strongly recommend it to anyone. Okay, so now let's get to the basics of convexity. And I will not give a lot of examples. I will discuss just a few examples and then move on because like this is not really the main focus of the course. We just need the definitions and a few properties. And I encourage you to look at the references if you are interested in other things. Okay, so what is a convex set? So a set, let us denote it by C, and let's assume that it is a subset of, it is a set in D-dimensional space. Like this D can be one-dimensional, or it can even be an infinite dimensional space, like the space of functions. Okay. So such a set is called convex if it satisfies the following condition. You look at any 2 points in this set, let's call them x and y, and then you look at the following quantity. So lambda times x plus 1 minus lambda times y. And for all values of lambda between 0 and 1, this combination of lambda times x and 1 minus lambda times y, this also belongs to the set C. If this property holds for any points x and y in the set and for all lambdas between 0 and 1, then such a set is called a convex set. Okay. And yeah, so I want to clarify the notation that so far we were looking at x as feature vectors and y as uh, the true price of the house. Going forward, we will look at x and y's as points in a set, okay, or arguments of the function. So yeah, like just bear that in mind. Yeah, so given this definition of convexity, like can you express this same definition in words? Like can someone take maybe 20 seconds and type what they intuitively see from this definition in the chat? Weighted average of x and y, right? So that is one way to look at it. So lambda times x plus 1 minus lambda times y is a weighted average. So Ankita says all points lying on the line segment between x and y also belong to the set. Right. So as several of you point out, Ahish, Nisarg, thanks. So that's exactly what this is. So we are saying that if 2 points belong to a set, and in this definition, the 2 points are x and y. So if 2 points belong to a set, then the entire line segment joining these points also lies in the same set. So because lambda can vary from 0 to 1, so if lambda equal to 0, that is point y, and if lambda equal to 1, that is point x. So the entire line segment joining x and y is supposed to lie inside the set C as well. Okay, let's look at a few examples. So even though the lines are not straight, but assume that this is a rectangle. Is this a convex set? Yeah, this is a convex set. How about this starfish shaped object? Is this a convex set? Right, so this is not a convex set. Okay, so then let me ask the following question. Okay, so let me draw the following set. So suppose this is the xy plane. This is -1. This is +1, comma 0. This is 0, comma 1. This is 0, comma -1. And suppose I draw the circle. So even though it might not look like it, but this is a circle. So this is x square plus y square less than equal to 1. Okay, so every point inside is also, but now I remove this point. So it's the set, it's the entire set minus the point 1, comma 0. Okay, so I'm looking at the entire circle except the point 1, comma 0 on the x-axis. And every other point inside the set, I'm looking at it. Is this a convex set? Think about it for 30 seconds. Okay, Abhishek and Devansh said no. I would encourage you to think about it for a few more seconds. Okay, so this is a convex set, and I would encourage you to area remains same after removing a point. That's not really the I can remove a point. Yeah, I can remove a point. So suppose I remove the center, the origin. Even then the area remains the same, but the set does not remain convex. Okay. So yeah, this is a convex set, and yeah, think about it a little. Uh, okay, another question. So how about this? Can a convex set have finitely many points? Yeah, so what Shivaya said is exactly right, that because 1 comma 0 does not lie on any line joining any 2 points. So that's why. Right, a set with a single point is a convex set. Okay, good. So then let's move on. So next, we are interested in something called a convex combination. So which looks like this. Let's look at n elements x1 to xn, and all of these belong to, let's say, d-dimensional space. And all of them essentially have to belong to the same space. And let's take any linear combination of these n points, which is of the following form. So we are looking at this summation ai times xi, I equal to 1 to n, where these weights ai's satisfy two properties. First, all of them are non-negative, and second, all of them sum to 1. Okay. In that case, such a combination of points is called a convex combination of these n points. Okay. So this kind of an object, this should remind you of something that you have seen in probability and statistics. So think of what this reminds you, and let's move on. So why we are interested in convex combination is that not really cone. So in cone, the summation need not be 1 as long as the weights are positive. Yeah. So this is exactly this is like taking an expectation, right? So this is like taking an expectation of a random variable which can take n values. Okay. So next, earlier we had defined convexity of sets in terms of 2 points. It turns out a set is convex if and only if it contains every possible convex combination of its points. Okay. So it turns out the two things are equivalent. Whether you impose the condition that for any 2 points in the set, the entire line segment joining them is also in the set. This is the definition of convexity. But you can also impose that you take any number of points in the set and come up with any possible convex combination of these points. This resulting convex combination will also be in the set. This is a very useful property of convex functions, convex sets, which like I will not prove. I will just state it as a claim, but excuse me. This is useful to remember. Excuse me. Give me a second. Okay, so now I think this is enough background on convex sets. Now we can move on to convex functions. So we are interested in convex sets in this course only because they are useful for understanding convex functions. Okay, so let's define what a convex function is. So given a function f, which takes points in d-dimensional space and gives out a scalar, uh, it is convex if two conditions are satisfied. First, its domain is convex. Okay, so the domain of the function has to be convex. So the domain of the function is any point at which the function takes a finite value. Okay. And the second condition is that you take any 2 points in the domain of the function and the following inequality has to hold. So you take a convex combination of x and y. Recall that if lambda lies between 0 and 1, then this is a convex combination. I hope that makes sense. So first we take the convex combination of x and y and compute the function at this point. And second, we compute the function at x and y. So let me remove this. Yeah, so second, we compute the function at x and y and take a convex combination of the function values at the 2 points. Okay, so these are the two quantities we compute. First, we compute a convex combination of the points and compute the function. Second, we compute the function first and then take a convex combination of the values. And the following inequality holds. Okay. So the function computed at the convex combination is smaller than the convex combination of the function values. Then this is a convex function. Okay. So the two quantities here, as you would have guessed by now, are, oops, that left-hand side is the function value at a point on the line segment joining x and y. So as we saw earlier, lambda x plus 1 minus lambda times y, as you vary lambda, gives you the line segment joining x and y. So on the left-hand side, we are computing the function value at a point on the line segment joining x and y. And on the right-hand side, we are looking at the line segment joining these 2 points. So x comma f of x, this is a point on the curve of the function, and y comma f of y, this is a point on the curve of the function. We are looking at a line segment joining these 2 points. And the following, and this inequality holds. So as Ikram pointed out, we are essentially looking at this picture. So given this curve of the function, we look at points x and y. We join them by a line segment. Okay. In that case, let's look at any point like this, which let's denote it by z, where z is lambda times x plus 1 minus lambda times y. So this is f of z, while this is lambda times f of x plus 1 minus lambda times f of y. Okay. So this is a function that satisfies this is called a convex function. The two conditions are its domain has to be convex, naturally. Okay, so one question, why do we want the domain of the function to be convex? Why do we want the domain of the function to be convex? Right, as Abhishek pointed out. So if yeah, this does not have to do with convergence, Archana, but as Abhishek pointed out, we want to compute the function value at this point. And this point will be in the domain only if the domain is convex. Otherwise, this is not guaranteed that this point will be in the domain and the function value would be well defined there, right? So that's why we want the domain to be convex. And second is that you draw the line segment between any 2 points on the curve of the function, and the line segment must lie above the curve of the function. Okay, so this is how we define a convex function. And yeah, so this is exactly what I just said. So based on my interactions with students, I have seen there are some misconceptions about the definition of convexity. So I want to clear some of them. So these are basically the definitions which students have given me when I ask them what convex functions are. So I want to like get rid of those misconceptions. So the first thing is that convex functions have unique minimizers. Okay. So there are uh, like, can you think of a convex function which does not have a unique minimizer? Square. So square and rectangle are sets. I mean convex functions. Right. So it should have a flat surface. And this is a simple counter example. So this is a convex function. You draw any like a line segment between any 2 points. For example, this, the function for any such line segment, the function lies between below the line segment. So this is a convex function, but it does not have a unique minimizer. Ankita says an upside down plateau. Right. Yeah, that's exactly this kind of function. That's a good example. Let's also look at a function which is not convex, but it does have a unique minimizer. Okay, so the counter example goes both ways. So, for example, this kind of a function. So, suppose it is growing. So, the minimizer is unique, but this is not a convex function because, for example, this line segment lies below the function. Okay. Is sine function a convex function? So Tanmay, what do you think? This is a sine function. So think about if it's a convex function. Okay. So this is the first misconception I've heard from students. The second is that f is convex if the second derivative is positive. Okay. So can you think of a counter example to that? That f is convex if second derivative is positive? Exactly, the same plateau example, because this doesn't have a second derivative, right? So both of these definitions, uh, yeah, both of these definitions don't give us convexity. The second definition is parabola also, right? Parabola would give you, right? So this is a parabola. So something like ax square with positive a. Second derivative would be 2a. It's positive. It would give you convexity, no? Okay. So yes, so these are the two things which I have seen students mention as definition of convexity, but both of them are like either wrong. So as in the first case, the unique minimizer, this is clearly wrong because as we saw in this example, this is not convex but has a unique minimizer, and this is convex but doesn't have a unique minimizer, or it's like it doesn't hold in every case. For example, this definition doesn't hold if the function is not differentiable or if it doesn't have a second derivative, right? So and a function need not be differentiable to be convex, as we saw in this inverted plateau example. Okay, so this thing one needs to keep in mind that this is the definition of convexity. Everything else which relies on differentiability or double differentiability, those are all like things that hold only under special assumptions. Okay, so let's look at a few examples. Uh, how about linear functions? So are linear functions or affine functions, are these convex if A can be any real vector and B can be any real value? Yeah, so this is a convex function. How about a quadratic function? Something like this. Something like this, where Q is a D cross D matrix and B is a D-dimensional vector. Is this a convex function? Depends. So I say it depends. Depends on what? On the eigenvalues of the matrix. Exactly. So F is convex if, so what, how does it depend on the eigenvalues of the matrix, Aish? So Abhishek says Q, if Q is invertible, it is convex. Okay, let's see. So let's assume that D is just 1. Okay. In that case, let me replace Q by a scalar Q. In that case, let me choose Q to be minus 2 and B to be 0, C to be 0. So my function is this. Is this a convex function, Abhishek? Right. So as Utkarsh pointed out, if Q is positive semi-definite, then this is a convex function. And now I leave it to you as an exercise that the linear regression mean squared error that we saw. When is this a convex function? And is it always a convex function? Does it depend on something, etc.? Okay, let's look at a few more examples. So how about fx equal to e to the ax, where a belongs to is a real value? Is this a convex function? Is this so Ankita, is this always a convex function or does it depend on the value of a? Purvi says if a is non-negative. What if a is negative? Okay, so both of you say that a has to be non-negative. Let's see. So if a is positive, you have something like this, right? And this is 1. If a is negative, you have something like this. Is this not a convex function? Yeah, so it is always convex. How about x to the a? Let's say the value is a is greater than 0. So how about x to the a? If the function is differentiable, can you not check if the function always lie above the tangent at any point? Sure, but then you require differentiability of the function. So like there are a number of definitions, number of tests for convexity, and it depends on what you assume on your function or what properties your function has. Depends on a. Okay, depends how? Right. So if a is greater than 1, then this is convex. How about a equal to 1? Oh, I think I should have specified, I assume x greater than 0 here. Yeah. Okay. So yeah, so these were some examples. Like I would encourage you to play with more. But now let's look at some properties of convex functions. Okay. So the first property is that if f is differentiable, now we are finally going to. So Ikram asks, if f function is discontinuous, will it be convex? That's a great question. Uh, so I won't be able to cover it in class, but I would encourage you to look at something called lower semi-continuous functions. Okay. So as the name suggests, it is semi-continuous. So this is not really a continuous function, but yeah, these can be convex. Okay, that's a very good question. Okay, so if f is differentiable, then I have the following equivalence. F, the function being convex, is equivalent. So this sign means equivalent, that the two statements mean one and the same thing. And the second statement is that the domain of the function is convex. As we have seen, we always require convexity of the domain. And the following condition holds. So if you take any 2 points in the domain of the function, then f at one of the points is lower bounded by this quantity. And what is this quantity? Can someone explain in words what this quantity is? The right hand side of this expression. Taylor expansion, approximation, gradient. So this is the first order uh, approximation. That is true. Anything else? Someone explained this thing about differentiable functions and convexity a few minutes ago. So this inequality is essentially saying that you can always lower bound a convex function by a first order approximation of the function, right? So any convex function you can lower bound by the tangent at a point. First order approximation uh, defined by gradient at a specific point. Okay. Okay. So these two things are equivalent if the function is convex and differentiable. So for this only holds for differentiable functions, that convexity is equivalent to this condition, that you can lower bound the function by a linear approximation. Okay, so let's look at a very good consequence of this property. And can you think of it? So in this inequality, if the gradient of the function is 0 at a certain point, what does that mean? What do we get if the gradient of the function is 0 at some point from this inequality? Abhishek, you are close. Think a little more about it. So this inequality has to hold for all x and y. Suppose you fix x. Suppose you fix x, and at that x, the gradient is 0. The left-hand side is still, you can vary y, right? Exactly. So Shivaya says that x, where the gradient is 0, is the minimizer of the function. Okay. So now we have this result, which you guys are familiar with, that if the gradient is 0 at a point, then at that point from this inequality, f of x tilde is less than equal to fy for all y in the domain. So wherever the gradient is 0 is actually the minimizer of the function. But this only holds for differentiable functions. If your convex function is differentiable, then if the gradient is 0 at a point, that point also minimizes the function. Okay, so you need differentiability for that point. Okay, so an example of this is the following quadratic function f or equal to ax f of x equal to a of x square. Here I should point out that a is positive, and you can verify easily that at x equal to 0 the gradient is 0, and that is the minimizer of the function. Okay, again, it doesn't say anywhere that the minimizer is going to be unique. For example, I can construct a differentiable function which has, for example, something like this. So if I construct a function so such that these edges are not sharp, in that case, the gradient is going to be 0 on a number of points. And these are all minimizers, but they are not unique. Okay. Think of this question. Maybe think of it in the break. So how about this function? What is the minimizer of this function? Okay. So we won't spend time. Minimizer would be saddle point, right? Or they are called something else. No, these are all minimizers. These are all minimizing the function. All this set of points, these are all minimizing the function. These are not saddle points. Okay, so let's look at another property, equally interesting and useful. Suppose the function is twice differentiable now. So not just differentiable, it is twice differentiable. In that case, f of being convex is equivalent to the following thing. So let's so f being convex is equivalent to, first, that the domain of the function is convex, and second, if you look at this matrix, so this matrix is called the Hessian matrix, and it's sort of the matrix of second derivatives. So Hessian matrix is denoted like this. It's a D cross D matrix that is symmetric, and all the entries, all the different entries of this matrix are the following. So if you look at the ijth entry, you compute the second derivative of the function. So first you differentiate it with respect to xj, the jth entry, and then you differentiate it with respect to the ith entry. Okay. And because the matrix is symmetric, this quantity is the same as, you can flip the order of differentiation and you get the same thing. Okay. So the second condition, if you have twice differentiability, the second thing you get is that this matrix is positive semi-definite. So this notation is for positive semi-definite matrices. Okay, so just hold on for a few minutes. If you don't recall what positive semi-definite matrices are, I'll discuss them in just a few minutes. But let me finish this point that if f is convex and it is twice differentiable, this is the same as the domain being convex and the Hessian being positive semi-definite. Okay. F being convex, doesn't it mean domain of F is convex? Yeah, so domain being convex is part of the definition. So like this is just stated for the sake of complex completeness, that the domain is convex and this condition also holds. Okay, so you can essentially focus only on the second thing. Okay. So what I'm saying is that if f is twice differentiable and it is convex, this is equivalent to the Hessian of the matrix, the Hessian of the function being positive semi-definite at all points in the domain of the function. So it's positive semi-definite everywhere. Okay. So just a simple case, a special case of this where d equal to 1 So for d equal to 1, look at this function. Look at this function. We have discussed this already. So essentially, what values of a lead this function to be convex? Abhishek also asked, why is it called Hessian? I am not sure. It must be named after someone named Hesse, I think. Yeah, that would be my guess. Some mathematician with the last name Hesse. Yeah, I'm guessing because Lagrangian is named after Lagrange. So, okay, thanks, Aish. Ludwig Otto Hess. Okay, so I see. Yeah, Hessian is a symmetric matrix. So as I said here, so under very minimal assumptions on the function like continuity, etc., this thing is going to be symmetric. So if it's twice differentiable, it is definitely symmetric. So whether you differentiate first with respect to j and then with respect to xi, or you differentiate it with respect to xi and then with respect to xj, this is the uh, it gives you the same result. So that's why it's a symmetric matrix. Okay. So to understand this condition a little more, let's take a small detour and try to understand what positive semi-definite matrices are. So this would also be a repetition for some of you, but let's do this just for the sake of completeness. Excuse me. So a D cross D real symmetric matrix is, so we'll talk about two related classes. One is positive definite and the other is a larger class called positive semi-definite matrix. Okay. So Abhishek says we are talking about D cross D matrix and continuity. I didn't get it. So what I said was a function of multiple variables, as long as it satisfies some minor continuity assumptions, its Hessian is symmetric. Okay. And because here the function, we have assumed it to be twice differentiable, all those assumptions are met. So we can rest assured that this Hessian matrix would also be symmetric. Okay. So now let's look at positive semi-definite and positive definite matrices. So given a real and symmetric matrix, if the matrix S is positive definite and it is denoted by this. So this is sort of an inequality, but with these curly inequality sign. And the matrix is positive semi-definite, positive definite if the following condition holds. So what it says is that you compute this quadratic term x transpose S times x for all possible values of a d-dimensional vector x. And as long as x is non-zero, this quadratic thing would be positive. Okay. And similarly, we can define positive semi-definite matrix, which also get this small equality below the inequality sign. And the definition is just a generalization of positive definite matrices. Here we allow the quadratic term to be 0, but this non-negativity has to hold for all values of x. Okay, so if this quadratic term is non-negative for all values of x, it's a positive semi-definite matrix. If it is explicitly positive for all x which are non-zero, then this is a positive definite matrix. Okay. So the interesting part about positive definite matrices are its properties, and you would be familiar with the. So given a positive definite matrix, all its eigenvalues are positive. Okay. And given a positive semi-definite matrix, all its eigenvalues are non-negative. So Ikram asks, is the right-hand side a scalar? So Ikram, where the right-hand side do you mean? Or do you mean the right-hand side here? Right. So Okay, so S is a D cross D matrix. So you tell me, what should X transpose SX for D-dimensional vectors? What should it be? Should it be a matrix? Should it be a scalar? Should it be a vector? Okay. Okay, so the first property is, for a positive definite matrix, all its eigenvalues are positive. If it's a positive semi-definite matrix, all its eigenvalues are non-negative. Second is a point about notation. So when we write with two matrices A and B, when we write this kind of an inequality, this essentially means that A minus B is a positive semi-definite matrix. Okay, so you will see this kind of inequality very commonly, and this is what it means, that the A minus B is a positive semi-definite matrix. So all the eigenvalues of A minus B are non-negative. Second, this third one also like sort of follows from first one. If A is positive definite, then A inverse exists and is also positive definite. This is quite straightforward. If A is positive definite, all its eigenvalues are positive. How is the and think how is the eigenvalues of A related to eigenvalues of A inverse, and then you can conclude how we get the third one. And finally, if A is positive definite, then there exists a positive constant delta for which this holds. Okay, so if A is positive definite, then all its eigenvalues are positive, right? If all the eigenvalues are positive, that means the smallest eigenvalue is also positive, and we can find a positive constant delta such that this holds, or we can also say that all the eigenvalues of A are greater than delta. This is equivalent, or we can say that A minus delta times ID is positive definite. Okay, so this was our detour of positive definite and positive semi-definite matrices. I will wait for 1 minute if there are any questions. Okay, so let me go through the questions in reverse order. So Karthik has this question that why are we using special inequality signs? So Karthik, these are not scalars. So we can use usual inequality signs when we are comparing scalars. So for example, here lambda I is an eigenvalue and we are comparing it against 0. Both are scalars, so we can use usual inequality signs. But here we are sort of comparing two matrices. Like, it doesn't make sense to compare matrices, right? So we compare them in terms of eigenvalues. So what this means is that A minus B is a positive semi-definite matrix. So sort of the eigenvalues of A minus B are all non-negative, or are all greater than equal to 0. So this essentially means that we are comparing the eigenvalues of A minus B with 0. Okay. So whenever you see this kind of special inequality, you can translate it to usual inequality in terms of eigenvalues. Abhishek has this question: how are convex functions and positive definite matrix related? So as we saw, Abhishek, in this result, whenever we have twice differentiability, then convexity is equivalent to the Hessian matrix, the D cross D Hessian matrix being positive semi-definite. Okay. So convexity is equivalent to Hessian being positive semi-definite. In the same way, like there is something called strict convexity. So let me, maybe I can write it here. So strict convexity means that the inequality that we had for convex functions, lambda x times 1 minus lambda x y, lambda times f of x plus 1 minus lambda times f of y for all lambda belonging to 0, comma 1. This was our definition of convexity. In strict convexity, there are a few changes. So you can make this inequality strict and you can make this interval open. So if lambda is neither 0 nor 1, then this equality becomes strict. So this is called strict convexity, as you can see, because the inequality is strict. And for strictly convex matrices, the Hessian matrix is positive definite for all x. Okay. So for convex matrix, convex functions, I think I misspoke. So just for convex functions, you get positive semi-definiteness of the Hessian, while for strictly convex functions, you get positive definiteness of the Hessian. Is there any significance of positive definiteness in deep learning also, or useful only for problems like regression? So that's a very good question, Rahul. And there is indeed a lot of significance of at least positive semi-definiteness in deep learning. So I would encourage you to look at like high dimensional statistics. So the regime where the model parameter is larger than the number of samples. High dimensional statistics is concerned with this regime. And in this regime, positive semi-definiteness appears very frequently. Okay. So there is actually someone named Parth Pandit. So Professor Parth Pandit in CMINDS at IIT Bombay. He has done a lot of work in high dimensional statistics of deep learning. There was one more question. So Ikram had asked, is there any special property of X bar? So I suspect, Ikram, you were talking about the X bars here. Is that correct? Yeah, so these can be any d-dimensional vector as long as they are non-zero for positive definite matrices. For positive semi-definite matrices, these can be any vectors. These can be even zero. These are just d-dimensional vectors, nothing else. Okay, so we needed this detour of positive semi-definite and positive definite matrices to uh, like justify this definition. We will at some stage return to this fourth property of positive definite matrices when we talk about strongly convex functions. So I will just state the name here. Strongly convex functions. So far we have talked about convex functions and strictly convex functions. So these were the strictly convex functions where the inequality is strict and lambda is in open interval 0, comma 1. We will get to strongly convex function either in the third session today or in the first session tomorrow. And there we will need this inequality. Okay. So far, just to recap, like what all we have done. So let me write this thing. So just to recap, we define convex sets and functions. We looked at some properties. These properties are for differentiable functions. We saw that gradient being 0 is the same as x being minimizer, and twice differentiability, meaning that the Hessian is positive semi-definite for all x. Okay. But something is strange here. Okay. And let me explain why. So, at least for me, the definition of convex sets is very natural. I'm just saying that look at any 2 points within the set, and uh, l- the entire line segment connecting these 2 points has to also be inside the set. So this is sort of like a property of whether the set is connected, as well as like whether there are any cavities in the set. So if you recall this example, this starfish, like there are sort of cavities in this set, right? So convexity, like a set being convex means that the set doesn't have any sort of cavities, right? So this is a natural definition, but the definition of convex functions, like this definition, this looks very unnatural to me. Like I don't know how they came up with this definition. I could not have come up with this definition myself. Okay. So uh, I came up with this idea that what if I define a new class of functions which has some nice properties, and let's see what that gives me, because this class of convex functions looks very unnatural. So that's what we are going to do next. There are some questions about textbook on high dimensional statistics. Okay, so uh, yeah, so Sandeep, I can give you two references. So one is Martin Wainwright has a big textbook on high dimensional statistics. I think it is called High Dimensional Statistics. And then there is someone named Philip Rigolet at MIT. I think both are at MIT now. Martin Wainwright used to be at Berkeley, but I think now he's also at MIT. So Martin Wainwright has a full textbook, while Philip Rigolet, he has lecture notes of his course on high dimensional statistics. I think both are named high dimensional statistics. Ahesh is saying the delta in the first inequality will be in the same as delta in the second matrix inequality. Uh, there is only one delta here, I see. I don't see any other delta. Yeah. Yeah, so getting back to the point I was discussing. So the definition of convex sets makes sense to me, that like we are defining some property about nice looking sets which don't have any cavity, etc. But the definition of convex functions, like I don't know how they came up with it. I couldn't have come up with it myself. Like it looks like an extension of convex sets, the definition of convex sets, but it's also very artificial looking. Like, why are we interested in functions which lie below the line segment at every point? So we are interested in these kind of functions. Why is that? Right? So I want to come up with a new class of functions, and which looks more natural. Okay, so I will give this class of functions some properties which I wanted to have, and then let's see what that gives me. Okay, so the first property I wanted to have is that we know that for any differentiable function, if a point x star is a local minima, then this property holds, that the gradient is 0 at that point. We know this holds for differentiable functions. Okay. So let us impose the condition that if a certain point, at a certain point, the gradient is 0, I want it to hold that that point is also the global minimizer of the function. Okay. So just to recap, I want to define a new function class, and I want it to have some nice properties, and I don't want it to look as artificial as the definition of convex functions. Okay, so that's the goal I have. I want to like come up with a more natural looking class of functions. So I begin with differentiable functions, and I know that for differentiable functions, at any local minima, the gradient is zero. So what I impose is that if the gradient is zero, for all the functions in this class, wherever the gradient is zero is also the minimizer. So if it is a local minima, it is also the global minima. Okay. So we know that this is true for convex functions, right? But it is also true for other functions. For example, if I define a function like this, here also, like it has a single global minima, and uh, local minima is the same as global minima, but this is not a convex function, right? No, I'm not talking about uniqueness. So notice that I have a belongs to sign here. I'm just saying that wherever the gradient is zero, this has to be one of the global minimizers of the function for all functions in this class. Okay, because I'm interested in minimizing a function, I'm interested in finding a global minimizer. So I want such functions where if the gradient is zero, that is also a global minimizer. That is the first property. Okay. The second property might look slightly mathematical, but trust me for a few minutes that it is a good property, and it is a not a very strong assumption. Okay. So this property is called smoothness. And what this means is that for a function, there always exists a positive constant such that the following holds. You look at any 2 points in the domain of the function, the gradient at these 2 points will satisfy this inequality. Okay. So you look at the difference of the gradients at these 2 points, you compute the norm of this difference, and it is going to be upper bounded by some constant times the distance between the 2 points. So I'm sort of saying that the distance between the gradients is bounded by the distance between the points up to some constant, up to some scaling constant. Okay. And this norm, if you don't recall, this is simple. Let's say this is simple Euclidean norm. Okay. So does anyone recall what this kind of a condition, does it have a name? This kind of a condition? Right, exactly. So I'm assuming that the gradient is Lipschitz continuous. Thanks, Aish. So the gradient I'm assuming to be Lipschitz continuous. This is exactly what we mean when we call a function smooth. Okay. This is, trust me for now, that this is a mild condition, and we will very soon see it in a lot more detail. Okay. Okay. So I have so far imposed just two conditions on my function class. So recall that I wanted to construct a more natural looking function class, not something like weird looking like convex functions. And the first condition was that wherever the gradient is zero, I want that to be a global minimizer of the function for all functions in that class. Okay. And the second is that my function, the gradient of this function is Lipschitz continuous. Basically, the distance between gradients at 2 points is bounded by the distance between that 2 points up to some multiplicative constant. And exactly, I'm imposing a restriction on how soon the gradient can choose. So basically, I'm saying that the gradient can be at most, the gradient can go at most as fast as a linear function. Okay. And this is a mild condition, like imposing this doesn't give me a lot. Now, here's the interesting thing. It turns out that given this class of function, so I'm saying that all the functions have to be smooth in this class, and the gradient being zero has to imply that the point where the gradient is zero is a global minimizer. It turns out for this class of functions, under very mild and reasonable assumptions. So I've listed these reasonable assumptions here. There are just two assumptions. I won't get into the detail here because like the reason is slightly technical, but the assumptions are very simple. Under very mild assumptions, it turns out that the class which I just constructed is exactly the class of differentiable convex functions. Okay. So the first time I saw this result, I was like blown away that I went along a different route, trying to construct a class of nice functions that I can minimize. Functions where if you are at a local minimum, you are also at a global minimum, and where you have some amount of smoothness, so the gradient cannot grow very quickly. And for such functions, this class of function is exactly the class of differentiable convex functions. So that's why it makes sense to study uh, differentiable, at least it makes sense to study convex functions. Now it turns out that here we are only looking at differentiable convex functions, and it makes sense to study even more general convex functions. But at least this is a more intuitive way to understand why we are interested in understanding convex functions, studying convex functions, and so on. Okay. So I think this is a good place to stop. So I can maybe take a few questions. I'm sure you would have some questions about what we just saw, because this is a highly non-trivial result. So just to, like, for the sake of completeness, these mild assumptions which I was saying, these are that, like, we want all linear functions to belong to this class of functions. And second, we want to impose the condition that if two functions f1 and f2 belong to this class, then you scale them by a positive number and add them together. This resulting function also has to be in the same function class. So sort of each conic combination of these functions also has to be in the same class. And these seem like reasonable assumptions. If two functions are in the class, then their conic combination also, you would expect them to be in the class. And linear functions are like simple functions. Why do they not follow from our two properties? What two properties do you mean? So Shiva, what two properties? Smoothness and global minima. So your question is, why does this result require these two conditions? I see. So it turns out the proof of this thing constructs special linear functions, and then you end up adding two functions. So there is some technical detail involved here, which requires these two. Uh, so can you explain them with an example? Like, explain what exactly? So, like, I want you to understand that here we are not constructing functions. We are actually constructing a class of functions. So, like, any example of convex functions that I give will be like, so you can very easily come up with functions which are smooth and where every local minima is also a global minima, right? But I mean, you can think of convex functions which satisfy both of these two conditions, but that would not justify this last statement. This last statement is about a class of functions. So, like, just giving individual examples of functions will not justify this statement in terms of class of functions. So, I can give you examples, but those will be like individual examples, while the statement here is about a class of functions. Why are we calling this mild condition? So why are we calling, you mean why are we calling smoothness mild condition, right? So the reason for that is we'll get to smoothness in a like after the break. But the reason I'm calling it a mild condition is that just smoothness doesn't give us much. So there is a result from 1987, I think, which says that if you try to minimize a function of this form, where you only assume smoothness, in that case, minimizing a general smooth function is an NP-hard problem. Okay. So, like, just assuming smoothness is not going to simplify our problem significantly. That's why I say that this is a mild condition. Because even if you have smoothness, the problem remains NP hard. Okay. Venkat asks, smoothness implies convex or independent? Good question. So it turns out that both of them are independent. Convexity doesn't imply smoothness. Smoothness doesn't imply convexity. Okay. But there is okay, this might not make sense, but I want to point it out anyways because it's so interesting. So first thing is that as you would notice immediately, smoothness requires gradients. So the function has to be differentiable for it to be smooth, while we saw that the function doesn't have to be differentiable for it to be convex. Okay, so that is straightforward. Now it turns out that there is a concept in convex analysis called Fenchel conjugate. Uh, so if it doesn't make sense, like ignore it, but I would state it anyways. Fenchel conjugate is pair of functions which are conjugates of each other in some sense, and their smoothness and convexity are related. So if you have smoothness for one function, you get convexity for the other function. So there they are sort of related, but the definitions are independent. A function being smooth doesn't imply that it is convex. A function being convex doesn't imply that it is smooth necessarily. Okay. Okay, so this is good. So let's take a break now. So how about we convene in so let's convene in 18 minutes. So currently this is 12:22 p.m., right? So let's reconvene at 12:40 and then we'll go for about 55 minutes to an hour and then we'll end for the day. Okay. So thanks everyone. We'll continue soon. Okay, so let's get started. So once again, I would ask you all to vote on how the pace of the course is. So I'll again post three options. Yeah, so if all of you can let me share my screen. Okay, so if there are any, yeah, I hope there are no more questions about what we have discussed so far. So essentially, we have so far looked at gradient descent, and so we began with the linear regression uh, in the first session, and then we realized that it is uh, yeah, I think recording of classes is made available after the course. I think so. Yeah, so we looked at linear regression and we realized that it's computationally very expensive if you have to compute the closed form expressions. So we went towards iterative algorithms, and gradient descent is one such iterative algorithms. We will discuss more such algorithms tomorrow. But first, we discussed some classes of functions because those are the classes of functions we will study and study how gradient descent performs in those classes of functions. Okay, so the first class of function we studied was convex functions. This many of you are already familiar with. So this is the definition of a convex function. And we looked at some of the properties of convex functions, like if the function is convex and differentiable, then you can lower bound the function everywhere by a linear function. And if the gradient is zero, that means we are also at the global minimizer of the function. We also saw another property that if the function is twice differentiable, then convexity is the same as the Hessian being positive semi-definite. Okay. And finally, like I said that the definition of convex function seems unnatural. So let's construct another class of functions where each local minima will also be a global minima and where we'll have smoothness. And we saw that this is actually the class of differentiable convex functions. Okay, so now finally we are ready to study gradient descent for a specific class of functions. All we need to do now is go back to smoothness, study smoothness in a little more detail, and then we will get to studying gradient descent. Okay, so coming back to smoothness, recalling the definition, recall that we saw that if the function is smooth, if for all points for any 2 points in the domain of the function, the following condition holds, that the distance between the gradients at the 2 points is bounded by the distance between the points up to some multiplicative constant L. And this essentially, as one of you had said, is means that gradient is Lipschitz continuous. So now let's look at some of the properties of smoothness to understand it in a little more depth. So it turns out that this definition of smoothness implies that at any 2 points in the domain of the function, the following inequality holds. Okay. So this inequality holds. So notice that on the left-hand side, we have an absolute value, and on the right-hand side, we have something that depends on the distance between x and y squared. Okay. So on the left-hand side, notice that we have difference between the function value and a linear approximation of the function constructed around point y. Okay. And on the right-hand side, we have distance squared. So let's open this up and let's look at what we get so if you have left absolute value on the left hand side, these are essentially two inequalities, right? So let's look at both these inequalities. So the first inequality is the following, that fx can be upper bounded by this quantity. Okay. And notice that this holds for all x and y. This holds for all x and y. On the right hand side, let us say we fix y. Excuse me. Let us say that we fix y. In that case, can you tell me what kind of a function is this right hand side? So if we fix y, y becomes a constant. In that case, the right hand side, like it's just a function of x. What kind of a function is it? So let's see. So if we fix y, this is a constant, right? Right, it's a quadratic function. So of y is a constant. Gradient of f at y is again a constant, but you have x here. So this is a linear term. And this with fixed y is a quadratic term. So if we fix y, we can upper bound our function f of x everywhere by a quadratic function, right? This is quite incredible. We are saying that fixing y and just varying x over the domain, the right-hand side is a quadratic function in x. And we are saying that at every point, our function f can be upper bounded by a quadratic function. This is quite interesting. Now let's look at the other inequality. So because this is absolute value, so we have another inequality, and this is that other equality. This is that other inequality, right? So essentially, this quantity is upper bounded by this, and it is lower bounded by negative of this. So this is the other inequality. Again, let's fix y on the left-hand side. What kind of a function is this in terms of x on the left-hand side? What kind of a function is it? So this, excuse me. This is a constant if y is fixed. This, again, the gradient is also a constant. It's a constant vector. So this is a linear function. And this is a quadratic function. With fixed y, this is quadratic in x. But notice that now this is a negative sign. So this is an inverted quadratic, right? So at each point, f can be lower bounded by an inverted quadratic function. So combining these two, the first inequality gave us that at every point, f can be upper bounded by a quadratic function, while the second gives us that at every point, f can be lower bounded by an inverted quadratic function, right? So combining these two statements, we have something like this. So this black line is our function f of x. You fix a point y, right? And once you fix a point y, we have a quadratic which upper bounds the function and touches the function at y. So notice that in both these inequalities, so in here, if we choose x equal to y, we get an equality here. So if x equal to y, this term goes to 0, this term goes to 0, and we have f of x. Right? Similarly, if we choose x equal to y, we get an equality here. So we have an upper bound of the function, which is a quadratic and touches the function at y. Similarly, we have a lower bound we have a lower bound of the function which touches the function at y, and it's a inverted quadratic. So at every point, we can both upper bound the function by a quadratic and lower bound the function by an inverted quadratic. Okay. Now thinking about it, we could have sort of guessed this property from this, right? Why is that? If the gradient is Lipschitz continuous, so look at this. The distance between the gradients is bounded by the distance between the points up to some multiplicative constant. So the gradient is Lipschitz continuous. It essentially means that the gradient can at most grow as fast as a linear function. So let me write it down. Gradient can grow at most as fast as linear function. Also, because we have absolute value here, so it can also happen that the gradient can decay as fast as a linear function. So gradient can either grow or decay at most as fast as a linear function. Okay. In that case, if the gradient, like think of a scalar, a function of a scalar value, if the function can grow at most as fast as linear and decay at most as fast as linear, in that case, what can we say about the function? The function can, in that case, grow or decay at most as fast as a quadratic function. Okay. Okay. Venkat asks, the true function can't go too far above or too far below your tangent line. So I think this is the right way to look at this. So this is the tangent line at y. It touches the function at y. And then you have this bound. Okay. Sandeep, so linear here is same as quadratic. No. So what I'm saying is that if the gradient, so this inequality says that the gradient can grow or decay at most as fast as a linear function. Okay. So think of it this way. If your gradient, let's say if dy dx of f is, let's say, at most a times x, then your function can be, or let's say like this, if f prime is at most ax, it grows at most linearly, then function can grow at most quadratically, roughly, right? So that's what I'm saying. Let me erase this because these are not very precise statements, but that's what I mean. That if gradient can grow at most as fast as a linear function, then the function, you integrate the gradient, the function can grow or decay at most as fast as a quadratic function. From where do we go this first property equation? You mean this? Next, this one. This is actually a consequence. So I'm not proving it here, but this is actually a consequence of the first one. Yeah. So actually, I can give you a reference for this. So there's someone called Yuri Nesterov who has done a lot of work in optimization, and he has this book called Lectures on Convex Optimization. And chapter 2 of that book is quite good. So you will find all of this in chapter 2. Actually, this thing that I just described before the break, that this class of functions is actually the class of differentiable convex functions. I read this in Nesterov's book only. So yeah, it's a very good reference. Okay, so smoothness gives us that you can, at every point, you can both upper bound the function by an upward facing quadratic and lower bound the function by a downward facing quadratic. Okay. Another property of smooth functions is that for twice differentiable functions, we can say the following. So recall that for convex functions, we saw that the Hessian was positive semi-definite. Here we are saying something else. Here we are saying that for twice differentiable functions, let's look at this first. So we are saying that Hessian satisfies this inequality, which means that L identity times L minus Hessian is positive semi-definite. So what can we say about the eigenvalues of the Hessian? What can we say about the eigenvalue of the Hessian given this? Not really. So what does this inequality imply about the eigenvalues of the Hessian? Not really. So all this means is that L minus eigenvalues of the Hessian has to be positive. That means all the eigenvalues of the Hessian has to be bounded by L. Okay. It doesn't say that they have to be positive. Note that these can be negative. This inequality, all this is saying is that they are upper bounded by L. Okay. If so, convexity is what implies this thing, but smoothness only gives you an upper bound, right? So I said earlier that convexity and smoothness neither implies the other. So we don't have this. We only have that the eigenvalues are upper bounded by L. Okay. If all the eigenvalues are upper bounded by L, in that case, I can also write it in this form. So what is this quantity? From your linear algebra classes, what is this quantity? Okay, so it turns out that for symmetric matrices, uh, this kind of a, when you have a symmetric matrix and you write your matrix in this kind of a two norm, then this is actually the largest eigenvalue of your, actually it's the largest absolute value of the largest value of the eigenvalue and absolute of that. So this is how it is defined. And I'm saying that the largest absolute value of the largest eigenvalue of the Hessian in absolute value is bounded by L. Okay. So for twice differentiable functions, the all the eigenvalues of the Hessian are bounded by L. And we also saw that you can always upper and lower bound the function by a quadratic. Okay. So it turns out, and recall that this L is the same as this L. So that's why this function is also called L smooth. So L smooth means the gradient is Lipschitz continuous with constant L, or if the function is twice differentiable, then the largest eigenvalue of the Hessian is bounded by L. Okay. So now we have defined convex functions and smooth functions. Is there any restriction on L value? Only that L has to be positive. Okay. So clearly, because here you have a norm on the left-hand side and a norm on the right-hand side. So this has to be a positive number. That's all. Okay. So now that we have defined convex functions and smooth functions, now we are ready to go to our first convergence result. Okay. So this is for gradient descent. And what the result says is the following. Suppose we want to minimize a function f. This function is convex. You recall the definition of convexity. This function is smooth. Just to remind you, this is what smooth means. for all x and y. In that case, if you run gradient descent, so if you run these iterations with this function at every given xt, you compute the gradient and move in the negative gradient direction. In that case, if you use your step size 1 over L, so note that L is the smoothness parameter. L is this smoothness parameter. If you use 1 over L as the step size, in that case, gradient descent after at any time step t would satisfy this inequality. Okay. So notice here, let me define a few things. X1 is initialization. This is where we began our algorithm. X star is a minimizer. So this is the minimizer of f. And it says, this inequality says that at any point, at any iteration t, the distance of the uh, current iterate xt from the minimizer in terms of function value. Okay, so what is the function value at the current point minus what is the minimum function value? This can be upper bounded by, you have a constant 2 times the smoothness parameter divided by t, the number of iterations you have run so far, and then you are multiplying by a constant, which is how far were you from the minimizer in the beginning. So where you began, how far were you from the minimizer? Are we referring to minimizer as global minimizer always? So what do you think? We are looking at convex functions. Yes, that's true. Okay, so let's look at this a little more closely. Okay, so first, note that uh, if you begin very far away from the minimizer, okay, so let's say this is your function. Let me draw a function here. So let's say this is the x-axis, and you want to minimize this function. Okay, so in one case, you begin here, right? So suppose this is your initialization, and in the other case, you begin here. So this is your initialization. In which of the two cases is it an easier problem to solve? In x1 or in x tilde 1? In which of the two cases is it an easier problem to solve? Right. If you are beginning closer to the solution, it's an easier problem to solve, which you naturally see here, that if you begin close to the solution, you have a smaller constant sitting here, right? So by running the same number of iterations, in the second case, your error would be smaller because this term is smaller, right? Okay. Other than that, you see a t in the denominator. So the larger you run your algorithm, the smaller your error will be. The closer you will be to realizing the minimum function value. Okay. And you also see a scaling in terms of the smoothness parameter L. Okay. So let's see why that makes sense. Okay. So, okay, how about this? So suppose I'm supposed to minimize a function f, okay, which let's say looks like this, what I've just drawn. And then I define a function f tilde, which is a million times f. Okay. So suppose the smoothness parameter of f is L sub f. Then tell me what is the smoothness parameter of L f tilde? Maybe let me repeat the question. So I have two functions. One of them is f, which I have drawn here. Okay. Another is a function f tilde, which is just a scaled version of f. I have multiplied f by a huge constant. Okay. Now let's say the smoothness parameter of f is L sub f. I'm asking you to give me what the smoothness parameter of L of f tilde is. And as Shivai said, this is exactly 10 to the 6 times L sub f. And this is very easy to see. If I scale up the function, I'm also going to scale up the gradients, right? So therefore, I will also scale up the L. Now let's look at this inequality. If I scale up my function by a large constant, then this gap will also go up correspondingly, right? This gap will also go up. And this should be reflected in the bound as well. So that's why I have an L sitting in the numerator. If I scale my function up by a large constant, if I scale my function up by a large constant, I should see a correspondingly larger error, and that is reflected by L. Just by scaling up the function, I am not really scaling up this distance because my initialization stays the same and my minimizer stays the same. I've just scaled up the function value, and that is captured by this constant L. So now we have seen the effect of the smoothness parameter. This controls the scaling. The initialization distance. This controls how bad was I in my initial guess. So this is essentially my initial guess of where the solution is. And if I guess very badly, I should pay some price in meaning that I should have to run more number of iterations. And then finally, this t in the denominator is what is the payoff of my hard work? If I have run this algorithm for t iterations, how close I am to the minimum value. Okay. Okay. So usually, if you read papers, etc., how can t be 0? I see. That's very easy to fix. So you just start your index from 1. Okay. So that's just an indexing issue. So sometimes people start t from 1. In that case, they have a 1 over t. Sometimes they start it from 2. In that case, they have t minus 1 and so on. Okay. Usually, you will see that in books as well as in papers, they state this result, but after going forward, they only state dependence in terms of the number of iterations, because that's really the only thing we have some intelligent control over. Like if you don't know anything about the function, you don't have an intelligent guess for where you initialize. You will either use random initialization or you will use origin as the initialization. So we don't have much control over this, or much intelligent control over this. We don't have much control over the scaling of the function either. Okay. So it doesn't make sense to scale down the function just so that the left hand side becomes small. That's not going to solve any problem. Okay, because the corresponding minimum value is also going down. So t is basically all we have control over, that we can choose to run the algorithm longer. So usually people state the dependence of the error in terms of number of iterations as big O of 1 over t. Okay. And the way to interpret this is to reach some target accuracy epsilon. So suppose you want this error, the difference in function value corresponding to the minimum value. If you want this to be smaller than epsilon, then what is the minimum number of iterations that you should run? Okay. So this is telling you that if I run my algorithm for t iterations, I would have error of the order of 1 over t. Okay. And another way to look at it is, if I want my error to be smaller than epsilon, then what is the minimum number of iterations I should run? So that's basically to make sure that this error is smaller than epsilon. A sufficient condition is I put this bound to be smaller than epsilon. Okay. So in that case, I would see that t has to be at least this quantity. Or again, dropping all the other constants, I can just say that I need to run at least order 1 over epsilon number of iterations to get a target accuracy of epsilon. Okay. What that means is that if I run for roughly 10 to the 3 iterations, about 1,000 iterations, I should get somewhere of the order of 10 to the minus 3 accuracy. So this should be a big O here. Okay. So this is all in big O notation because I'm hiding a lot of constants. I'm hiding this L, I'm hiding this thing. Okay. So this is my like the kind of convergence gradient descent can give me if I'm running uh g- if I'm solving a smooth and convex function. Okay. So any I'll stop for a minute for any questions. Okay, I think there are some questions here. So let me go in order. To attain 1 by 10 accuracy, need to run 10 iterations. Like, so please note that all of this is absorbing a few constants here. Okay, so that's why I'm stating everything in big O notation. So usually, like, the accuracy you need to achieve has to be a small enough number. Okay, if it's something like 0.1, then these constants might have a large influence. But if it's a very small number, then it is unlikely that these constants will have a large influence. Okay. Uh, you are in, okay. If learning rate is too high, loss function overshoots the minima. If learning rate is too low, large number of iterations are needed. So Ikram, that's completely correct. So this choice of step size is very crucial. Tomorrow, I will show some experiment results where we will play with learning rates and uh, exactly see the thing that you are pointing out, that we might not converge if the learning rate is too high, and we might converge very slowly if the learning rate is too low. Purvi, accuracy, you mean an error in the order of... Yeah, so by accuracy, I meant that I want this error, this difference between f of xt and f of x star to be smaller than epsilon. Uh, can you please explain the target accuracy again? So Venkat, do you still have this question or should I? Okay, okay. Uh, prepare for the... Okay, so yeah, I'm not sure if yeah, NPTEL, I don't know when NPTEL guys provide these recordings. If it overshoots, should it change the direction back towards the minimum? Uh Right. So because we are working with negative gradients, it should, but it's not guaranteed if the step size is too large that this changing direction would have a sufficient impact. Okay. So I think like this point will become a little more clear when we discuss it tomorrow. So hold that thought for now. Okay. Okay. So now let's continue. So we have seen the smooth plus convex case, uh, and we see that this 1 over t convergence is what we get. So now I want to like go to a different class of functions and let's see what we get from that. Okay. So now I will have to write because I did not write on my iPad. I just have paper notes. Okay. So next we look at a class of function called strongly convex functions. So I alluded to this earlier once, but let's see what this means. So recall that convexity means the following, that this thing holds for all x comma y in the domain of f and lambda in 0 comma 1, right? Now, it turns out that what strong convexity demands is something stronger. It says that if g of x defined as f of x minus is convex, then g is mu strongly convex. So what that means is that I don't just want convexity. I want that even if you, uh, sorry, let me correct that. Then f. So I don't just want convexity. I want that even if I take away a quadratic function from my original function f, the result should still remain convex. Okay. So in words, f is at least as convex as a quadratic function. Okay. So the function has to grow fast enough that even if you subtract a quadratic function from it, it still remains convex. Okay. So let me describe a consequence of this, and then maybe things will become a little more intuitive. Okay. So we'll come back to this figure in a bit. Let me drag it down and then talk about a property of convex functions, of strongly convex functions. So it turns out that if f is differentiable, then for all x comma y belonging to the domain, the following holds. Or maybe I should state it with the opposite notation. Oh, I have already stated that. So what this is saying is that if a function is strongly convex, and it is differentiable, then the following thing holds. Okay. So can someone explain in words what this means? So on the right hand side, fix y. Then what kind of a function is this on the right hand side? This is a quadratic function. Thanks, Ikram. This is a quadratic function in x. So now I'm saying that at every point x, I can lower bound the function by a quadratic. Where have we seen this before? Have we seen this before? Smoothness. But what was the difference? What was the difference? Okay, what else? So smoothness was, okay, or maybe I should write it here. So smoothness was that at every point I can upper bound the function by a positive quadratic, and I could lower bound the function by a negative quadratic. Okay. So this figure exactly shows what it means. Uh, Actually, it doesn't show smoothness completely. But the point is that with smooth functions, sure, you had a quadratic lower bound, but it was an inverted quadratic. Now I have a quadratic lower bound, but it's an upwards quadratic. So I'm basically saying that my function f grows at least as fast as quadratic. Okay. So earlier, if you recall the figure from smoothness, my function was sort of sandwiched between two quadratics, an upward facing quadratic and a downward facing quadratic. Okay. Now I just have a lower bound that at every point, if you notice this middle figure, at every point, I can lower bound my function by a quadratic. Okay. So convex functions mean that at every point, I can lower bound my function by a linear function, right? Defined by the tangent. Strong convexity gives me something stronger. It gives me something stronger about the growth of the function. At every point, I can lower bound the function by a quadratic function rather than a simple linear function. Okay. So strong convexity gives me at every point I can lower bound the function by a quadratic. What if I have strong convexity plus smoothness? What does that give me? So what if f is strongly convex and smooth? That's exactly right. So Utkarsh says that so strong convexity gives me quadratic lower bound. Note that this is upward facing quadratic, and L smoothness gives me quadratic upper bound. And note that oops, this is also upward facing quadratic. Okay. So if I have a function which is both strongly convex and smooth, it is lower bounded by a quadratic, it is upper bounded by a quadratic. Okay. Now tell me then what should be the relation between mu and L? Exactly. So just as Abhishek and Rahul say that I necessarily need mu to be upper bounded by L. Okay. So this is one property of strong convexity, that I can lower bound by the function by a quadratic. Another property which will also look familiar to you is if f is twice differentiable, then for all x belonging to the domain, the Hessian satisfies the following condition. So now that we have seen smoothness, remind me, what does this mean in terms of eigenvalues of the Hessian? Something more than that. Upper bounded by mu. Think again, look closely. Lower bounded by mu. Exactly. All the eigenvalues of the Hessian are lower bounded by mu. And that's why if we have smoothness and strong convexity, so I'm being a little lazy. In that case, what can we say about all the eigenvalues of the Hessian? What can we say about all the eigenvalues of the Hessian if I have a function which is both smooth and strongly convex? Right. So this is lower bounded by mu and upper bounded by L for all x. Okay, great. So now we are ready to state the convergence result for gradient descent for this class of functions. Right. Mu lies between 0 and L. Does it mean the ratio of mu and L is significant? Hold that thought for just a few minutes, and then hopefully you will have the answer to that question. So let me see. So this was let me copy a few things from here so that I don't have to write again. I think so this is the second result. I have L smooth and I have strongly convex case. So this is strongly convex and this is L smooth. Okay. So in this case, again, with eta equal to 1 over L iterates which are xt generated by gradient descent satisfy one minus 1 over kappa times f of x0 minus f of x star. I think I should say f of x1 just to be consistent because I said that in the previous result. Here, kappa is, to answer your question, Venkat, is the ratio of smoothness and strong convexity parameters, and this is called condition number of F. Interestingly, we can also say something about the distance to the minimizer. So you can show that the distance to the minimizer, oops, I should write x1. Okay, so what does this mean? This means that if I run gradient descent, so I will not, shouldn't the condition number be ratio of maximum eigenvalue to minimum eigenvalue and not the ratio of bounds? So, right. So I'll come back to your question in just a minute. Let me explain the result first. So if we run gradient descent with this step size, again, this is also the step size that we used in the smooth and convex case. But if we run gradient descent with this step size, then the iterates of gradient descent satisfy this, that the difference in function value between xt and the minimum function value, it satisfies this bound. Notice that compared to how different the function values were in the beginning of the algorithm, the difference is shrinking exponentially fast at each iteration. So kappa, because we just saw that mu is less than equal to L, so kappa is greater than equal to 1. Therefore, this quantity 1 minus 1 over condition number, this quantity is less than 1. So this quantity is less than 1. This is actually exactly less than 1. And therefore, compared to the difference, this difference at the first iteration, at each subsequent iteration, the difference shrinks by a constant value, right? It shrinks by a constant value, which is exactly 1 minus 1 over condition number, which is strictly less than 1. That is one thing. The second thing is, when we were looking at the smooth and convex case, we could only bound the difference in function values. But here, we can bound the distance to the minimizer as well. So compared to the distance to the minimizer initially, notice that the distance after t iterations falls exponentially. So the distance is shrinking by a constant factor at every iteration. Okay. So distance shrinks by constant factor at each iteration. Okay, so now to get back to Ahish's question, shouldn't the condition number be ratio of maximum eigenvalue to the minimum eigenvalue and not the ratio of the bounds? Okay, so that's a good question. So if you have a smooth function that is also strongly convex, these bounds hold for all eigenvalues, but there would be some eigenvalue which would be exactly L, and there would be some eigenvalue which would be exactly mu. So having a mu strongly convex function means the minimum value is exactly mu, and having an L smooth function means the maximum value is exactly L. Okay, so we do have equality. So this is actually the condition number of the Hessian matrix, because the largest possible eigenvalue of the Hessian is L, and the smallest possible eigenvalue of the Hessian is mu. Okay. Any other questions? Distance is also shrinking exponentially in every iteration. Kappa is constant, but shrinking seems to be exponential. Okay, so think of it this way. So kappa is a constant, but this quantity, so let's take some concrete numbers. Let's say, so kappa has to be greater than equal to 1. Let kappa equal to 10. Okay, in that case, 1 minus 1 over kappa is what? This is 0.9. Okay, so let's look at this inequality. So at every iteration, the difference between the function value and the minimum value can be bounded by this quantity. So suppose initially this difference was, let's say, 5. Okay. In that case, after t iterations, it would be 0.9 to the t times 5. Right? So at every iteration, the distance, and if you look at this thing, at t minus 1 iteration, this is actually shrinking by a constant amount. So if you look at the proof of this, you get something like this. So at every iteration, the difference is shrinking by at least a constant amount. Okay. L smooth plus mu strongly convex gives a unique minimizer. You tell me. By the way, iterations, it's only been factored by 0.9. I don't understand the question.
No, sir, just got it. Like I was saying, between iterations, it's only been kind of factored by 0.9. Like,
Yes, yes, yes. So Shivai, think about your question a bit more and think if you even need smoothness. Okay. Okay, so I think that's where we will end today. So we have today's, like, just to recap, uh, we began with linear regression, and at some point we realized that closed form is expensive. So we need iterative updates in the hope that they would be cheaper. That brought us to gradient descent. We first introduced the algorithm, and then we decided that we will study this algorithm. So we introduced convexity, we introduced smoothness, and using these two, we analyzed convex plus smooth functions under GD, and we saw that the error decays as 1 over t after t iterations. And then we looked at strong convexity. And for these two, strong convex plus smooth, we realized that error actually falls exponentially. Okay. So we will continue from here tomorrow, and we will look at some more advanced algorithms and what makes modern algorithms more scalable. Okay, so I can stay for a few more minutes if there are some questions. Uh, yeah, I will send the notes as soon as possible right after the class. I don't know when the NPTEL folks will share them with you. Yeah, that's not really uh, in my hand. Or what I can do is the following. So I can post these notes on my website, and you can yeah, you can download them from my website. Okay, at least I can do that. So let me post the link to my homepage, and yeah, so this is the page on which I will post these lectures. Okay. Okay, thanks, Utkarsh. Yeah, any questions? I'm happy to stay back. What happens if kappa is very large? That's a great question. And if kappa is, so actually today we didn't get time to look at how how many iterations we need to run to get to a specific accuracy epsilon. Tomorrow we'll do that first thing, and then we will realize that your concern is very much valid. If kappa is very large, the number of iterations grows linearly with condition number. So we will very briefly look at an algorithm which helps with that. I'll see if I can get to Adam W. Uh, yeah. So if there is interest, like within after a few months, I would be happy to teach a follow-up of this in which we can go into those things in a lot more detail. Federated learning, I do plan to cover. Do the loss functions that we use, are they ever going to satisfy these requirements? Yes, they do. So there are a number of problems in which you have convex losses, and then if you add a small regularization, the loss becomes strongly convex. Okay, thanks everyone. I will see all of you tomorrow.